UW-Madison Computer Sciences Department. We're glad you could join us this morning. And the first order of business today is the welcome from our department chair, Remzi Arpaci-Dusseau. Will be speaking before the faculty talks, and I'm just going to turn it over to him right now.
All right, cool. You're going to have to stop sharing, which you have now done. Thank you. Okay, can everybody see that?
We can.
Thanks. Welcome. So welcome to everyone from wherever you are. Appreciate you joining us. I'm here in my office in Madison, Wisconsin, and my name is Remzi Arpaci-Dusseau. I've been a professor here for 22 years, and I'm currently the department chair. So welcome. We're really excited to meet you and get to talk to you a little bit about what it might be like to be a student here at the University of Wisconsin-Madison. So I've just structured this talk around this one basic question, which is why come to UW-Madison? It may be a slightly biased presentation, but I assume you might assume that. So I'm going to give a few reasons. First reason, place. Actually, Madison is just a beautiful place to live. Simple reason. You can see it's actually situated between two lakes. The campus and the downtown kind of merged together. Just a wonderful place to live. In fact, it's often voted #1 place to live in many surveys and magazine articles. And oddly enough, it's been voted the #1 place to live in case of extreme climate change. So you have that going for you too. Number two, has a great history. Fantastic history here. There's actually a prehistory I've been learning about more. There's some undergraduates here. One of them, John Bardeen, went on to create the transistor. Another, Grant Gale, went on to play a key role in the formation of Intel. And Gene Amdahl was one of the first computer architects, was a student here. But the history of the CS department, so that was before the CS department even existed. But the history of CS is amazing. Like the second CS department in the country, some foundational thinkers, mentioned even in this letter I quote from Alan Turing to his sister, talks about people who are professors here. And then the next generation really practically created whole areas of computer science. And of course, why does this matter to you? Well, it's cool, but it also, like, those people hired some of the people who are here, who hired the next generation of people and so forth. A third reason beyond history is research. And this is really something that you're going to hear about in great detail in the whole morning. So to some extent, there's no reason for me to spend much time on it. There's many huge projects going on. We do really well if you look at like CS rankings and the areas where we have people. We don't cover all areas, but in the areas we do, we have really productive researchers. And you'll hear about that in great detail. I think everyone who's here loves their research. One thing you also won't hear about is that there's a train that goes by. We are near a train track. So if you hear that in the background, it's something also to look forward to. In any case, another reason, education. We have great classes. When you're taking classes as a graduate student, there's really kind of two types of classes. Like upper level undergrad, classes are like 500 or 600 level. Those are great for foundational knowledge in a particular area. Graduate classes, 700 level higher, connect you to latest research in areas. And of course, give you some idea of what not only the latest work, but what the faculty here are doing. We have fantastic people. I think that's true across the board. That's the people you're working with, that you're learning from. And, is that really loud, by the way, the train? Yeah, so
we can hear it, but we can hear you just fine.
Okay, great. But it's just such a CS department thing, is that there is that train track there. And, I'll be teaching class some days and the train goes on by and we all sit there awkwardly and wait for it to blow its horn. They blow the horn, by the way, that's by law, so that they don't run over people. So people know the train is coming. So in any case, the people matter and all sorts of people matter. Professors you're taking a class from, but really students too. You learn so much from your peers, the students that are around you. And I urge you to take advantage of that when you're here. Get to know people, because you'll learn, in watching someone work for a minute, you'll learn so many things about how to be a better computer scientist. And of course, our staff too. You've met some of them this morning, and I think they're all fantastic. We're lucky to have them. In our faculty, I just listed some recent awards they've gotten. Faculty here tend to be highly recognized in their fields. Too many awards to go through, but they're all amazing. We're growing, so you can see this is a current group, and then below is kind of what we hope to do over the next many years. So we have a lot of growth ahead of us. We're actively in a hiring season right now. Hope to hire 3, 4, 5 more people just this year. Of course, we have many wonderful staff. I listed some here that are important for grad students, like Angela, grad program coordinator, Jana, professional program coordinator, David Parter in the CSL, Computer Systems Lab, for help with that. Nebadita's, of course, been helping a lot with getting you into this program. And then Hillary with payroll and travel. And then Cindy Fendrick, you also saw at the beginning, she's kind of in charge of all of our academic services. Fantastic staff, very lucky to have them. And I, as a chair personally, very lucky to work with all those people. Students, too many to show their pictures. I think that we have so many fantastic ones. Because it was easy for me, I picked some of my former students who have gone on to be, directors and professors and engineers, and just if any faculty you ask them about their students, they'll tell you about how fantastic they are. Final couple things. We actually have a new school on campus, which you're wondering what that is. It's called CDIS, the School of Computer Data Information Sciences, and the computer science department is in that school. Now, for the most part, as a student, the department you're in matters the most. So CS department matters most. But why this school matters to you, with its new director, Tom Erickson, and why it connects us to statistics and the iSchool, those are the other departments in the school, is it means that we're going to have so many more things going around on campus around computing, around data, just around the technology field in general. And so I think you'll see a lot of effects of that, even though, like I said, most of what you care about is going to be within CS. One final outcome that's actually one of the earliest, and now there's a ambulance going by or a fire truck. It's like kind of comical. What other, could there be like a tornado in the background too? That would be the next thing that happens. The one tangible outcome is what I'll call architecture of the school. Because once we created the school, the first thing we said is, how do we house the school? Where do we put the school? And so we've been working very intensely on a new building. We're in a design phase, ending of a design phase right now. And in the summer, right across the hallway, across the train tracks, literally on the other side of the train tracks, they'll start demolition at the site of this beautiful new building. You can see it there, kind of situated between a couple of others. It has, basement, first floor, second floor is really around students, student services and classrooms. And then floors 3 through 7 is all research, the research tower part of this building. It's going to be a wonderful space. It's going to bring us together in a way that our current facilities don't. And it's happening right now. So if I were summarizing, you should come to Wisconsin, of course. And there are many reasons: place, history, research, education, people, school, architecture, which is, ends up as this acronym, FREPSA. But I realize that if you just rearrange it slightly, it becomes a different word, which is perhaps, which means perhaps you should come to Wisconsin. So I shouldn't have done animation on this. Perhaps coming here is the best choice. So thank you very much. I look forward to meeting some of you in the afternoon. And I think I will just hand over to one of our esteemed professors, Bart Miller, who will talk about the area that I work in and that he works in, my close colleague. Let me figure out how to stop sharing. All right.
Thank you, Remzi.
Oh, thank you. All right.
Okay.
I will see you all. Yeah.
Let's see if I can get the wonders of Zoom working. Are we all up, and you guys can see my slides now?
Yes, we can see operating systems.
Okay, great. Well, good morning, good afternoon, good evening, good night, depending on where you're sitting, or maybe you're lying in bed all cozy. It's, I've got my coffee here to figure out what time of day it is. And welcome to Madison. Sorry that most of you can't be here. So for today, you're missing out on a great scoop of ice cream from the excellent Babcock Hall ice cream on campus, or a glass of legendary Spotted Cow beer, all sitting on the lakefront at the Union Terrace. So hopefully we'll do that all in person together soon. So let's talk about the systems area. And of course, machine learning and big data get a lot of attention today, but there's so much going on in systems that's new now. And so it's definitely worth thinking about. And of course, the operating system doesn't work, nothing else works. So we're kind of essentials. So I'm going to talk about two things today. The first is systems research in general. So if you haven't thought about systems research, what it is. And the second is what we're doing here, what our various faculty are doing here. So let's go back. Let's go back in time to the early days of OS research. If you remember studying semaphores in your undergrad operating system class, you may have heard the name Edsger Dijkstra, one of the great early pioneers in operating systems. And you know, he was, you know, back when people saw you guys are just engineers, whatever that means, you know, he said the intellectual level needed for system design is grossly underestimated. And this type of work is very difficult, and that every effort to do it other than with the best people is doomed to either failure or moderate success or enormous expense. So it's been recognized for a long time just how interesting and challenging this area is. You know, if we go forward a little bit in time, Butler Lamson wrote a beautiful paper called Hints for Computer System Design. And he, like the others, were concerned with coming up with principles, with abstractions and techniques that would go on to apply to all the work we're doing forward. You know, Butler said things were complicated because we have these big external interfaces that aren't very well defined. The systems have complex internal structures. When you do a demo in the operating systems area, it's often not very dramatic because there's a bazillion interesting things going inside, but you don't see them. And that's what we do. We hide the hard stuff. And Leslie Lamport talked about distributed systems in a really cute way. He said a distributed system is one which the failure of a computer you didn't even know existed can render your own computer unusable. And he wrote this long before we were all struggling with the internet. You know, of course, we all know about major landmarks like Unix and C that came out of Bell Labs in the 70s. And then the local area network, the mouse, window-based systems that came out of Xerox Palo Alto Research Center, Xerox PARC around the same time. And of course, Linux is a direct consequence of Thomson and Ritchie's work on Unix and this other work. So we're built on some very important early pioneering. And interestingly enough, there's still the same level of problems going on today. Also from Xerox PARC in the 70s with the idea of a file server, which we all take for granted now. And there, that industry has grown. We have interesting things like storage appliances and kind of cool. Remzi and Andrea, who two of our great OS faculty, are real leaders in the area of storage. So if storage, the underlying structure of where the data is housed and how to get it, is interesting to you, we have a couple of world leaders here in that area. Of course, virtualization. In the earliest days, we realized we had to virtualize memory, but then it's been the key to providing stronger security and performance isolation. And that's been a key to enabling things like cloud services. We ended up with virtual machines, first commercialized by VMware in the late 80s. Not too many years after, open source versions of things like Zen came out. And then more recently, we've got these ideas of these lighter weight forms of isolation called containers. And Docker is probably the best known, but there's many, Kubernetes, Singularity, and many other instances of that. But you know, by the way, if you haven't studied it, there's no such thing as like a container call or system call inside of an operating system. It's a collection of interesting operating system security features, some of them classic and some of them are much newer, constantly developing. So in order to build containers, you have to know a lot about different things that go on inside the operating system. So these are some of the foundations. Of course, scale, many things, making things work with millions of cores is a whole new ballgame. Things like the Google file system and the newer version Colossus, and MapReduce made computing and data handling at scale possible. The question of big data couldn't exist if there wasn't a system underlying it to handle that. And then here in Madison, Moreau Livny's HD Condor project introduced high throughput computing, showing how to give you millions of CPU hours over a single weekend. You need to compute, you need to train, you need to do some kind of scientific analysis to do it. And actually my group works with supercomputers, the biggest ones in the world. So my students regularly have access at their desktop to 5 million cores in a single run. And they think as tiny run as 50,000 cores. So, and there's a really interesting convergence of high performance computing and data center computing. And of course, this scale has enabled so many. This scale has enabled so many important things like big data analytics couldn't do without these underlying structures, and training of these incredible new learning environments couldn't be done without these things. Okay, so let's talk a little bit about what's new in system research. And of course, we sit right in the middle. We sit on top of the hardware, and we have to use or suffer, depending on how you look at what the architects give us. And we have to provide something sensible and usable to the applications people. So the boundary. So one of the really interesting things that's changing. So basically, almost everything you learned in the undergraduate operating system class is going to be obsolete soon. And you can be on the front edge of figuring out how to do that. Non-volatile memories are growing from just a simple flash drive to memory technologies like Intel Optane, which are almost as fast as RAM, but are persistent. You don't lose the data when you turn them. So the boundary between RAM and disk is disappearing. So how you design virtual memories, how you design file systems, all the things you learned is up in the air and is being rethought right now. So this is really a fascinating trend, and it's an exciting time to get in on such radical technology changes. And we're dealing with not just CPUs, GPUs, TPUs, but for machine learning, tensor processing units, and FPGAs, custom programmed hardware, and designing this heterogeneous hardware and integrating it into a uniform model and trying to figure out what the memory models look like. If you've heard any GPU programming, you know what a total mess the memory models are. And so there's just a ton of work trying to figure out how do we provide the system views for all of this. Okay, so we have this really great team of incredible researchers, and I'm also very proud to say fantastic teachers. And so Andrea and Remzi are working on high performance storage, new file system architectures, distributed storage, consistency, reliability, file system reliability, concurrent systems, and decentralized systems. That sounds like a real mouthful, but they're really at the center of how storage works. My work covers the area of performance of high performance computing systems. We build tools for systems, as I said, with millions of cores. And I said my students regularly get access, experiment on programs that have 5 million. Yeah, 5 million cores. And I'm interested in system and tool support for heterogeneous systems, things like CPU, TPU, GPU systems. Mike Swift's research focused on the gap between hardware and operating systems, such as how to improve reliability and performance of hardware access, while trying to simplify the programmer's task accessing the hardware. His work covers most of the major hardware in the computer center devices. Mike did a lot of groundbreaking work in device drivers. Beyond that, memory storage, network, and CPU. And he looks at work of proposed new hardware design and tries to anticipate what systems level issues will arrive and try to be ahead of the curve. He looks at newly released hardware and tries to figure out how to design abstractions to better use those, things such as new protocols for RDMA, RDDMA, or to leverage programmable network switches. And he also looks at standing issues in systems that have been worsened by technology trends, such as trying access to terabytes of virtual memory. The page tables you knew just don't scale the way they do. So Shivaram's research is focused on developing systems for machine learning and data analytic workloads. So his recent research includes building systems for learning ML models and resource managers that can fairly share resources. So Shiv lives right at the boundary of machine learning and operating systems and how to leverage that. If you look at computer science rankings, like people like to look at these rankings and publications, you look at you put together all the top operating system conferences, we come out actually on the top of that list. And as a grad student participating in research, your impact is by typically what you publish and to some extent what software you develop. And it's nice to know that we're right there, very close to the top. And this is just a partial list of some of the papers that our research assistants, graduate student research assistants have been producing. And you see top conferences like SOSP and OSDI, the classic top, ASPLOS, on the border of operating systems architecture, things like ML, SIS, that's on the border of machine learning and systems, FAST, which is the top conference in storage. So you can see, and then we're well represented in top journals, IEEE transactions on this and that, ECM transactions on this and that. So not only are we doing interesting projects, but the work is getting out there and being recognized by our peers. And these are all grad student authors. Okay, so our students end up in all sorts of interesting places, in academia, top industry research labs, plus tons of development areas, startups, and government labs. And you can see the full list online. We cover, as I said, if you look at the stack of how a system looks and is designed, different members of the systems group cover different areas. You can see storage, of course, non-volatile memory techniques. We see, which is just incredible, important new area. You see Mike Swift in there, reliability, consistency of storage, and just about anything else interesting with storage. You see Remzi and Andrea. We see systems needs machine learning, graph learning, distributed machine learning, systems support for learning. Of course, that's we see Shivaram's work in here. Cluster computing, Shivaram's done a lot of work in stream processing. Tools, how do you monitor and debug things at the scale of these data centers? And that work that I'm doing, high performance networking. And now, if you're interested in talking with us, we have 2 sessions online. You'll see on the online schedule, meet our system students, and that later today and early tomorrow, and one-on-one with faculty. And just as a personal note, I have some other, let's say, security government obligations this week. I'm actually not in Madison or even in North America right now. So if you'd like to talk with me at all, just send me an email. We'll set up a time to talk. And I think that's a wrap with 2 minutes to spare.
Thank you, Bart.
And I'll stop sharing. Okay, take it away.
So the next talk up is going to be by Karu Sankaralingam, and he's unfortunately not able to join us today and has recorded his talk. So in just a few moments, that recording will begin, and you'll find out all the exciting things that the computer architecture people at Wisconsin are doing.
Angela, can you confirm that the video is showing?
Not yet.
Is it showing on the screen that a video is ready?
I have a black screen.
Same here.
Okay, I will start and we'll see. Can you see the images?
It's there now. I can see the image.
Hi all, welcome to the grad student visit day. I am Karu Sankaralingam. I am here to talk about the computer architecture group, and it includes myself, and the other professors are Swami Tanu, Miko Lepasti, Joshua San Miguel, Matt Sinclair, and Guri Sohi. So I'll begin by telling you 10,000 feet what we do, and my goal with this talk is tell you why you should come and join here and do great research with the rest of us here. So if look at microprocessor evolution, the first microprocessor was built in 1971, Intel 4004. And for about 3 decades or so, there was this big uniprocessor revolution of building faster and faster microprocessors, but with just one processor core. Several techniques were invented at UW-Madison by Sohi, Smith, Goodman, Hill, and Wood, like branch prediction and so on, that went into this revolution that made computers what they are today. Most recently, we've seen these massive multi-core chips, AMD EPYC as an example, and super high performance chips from Apple going into their laptops with the Apple M1 processors, and also accelerators in form of the Google TPU and NVIDIA's AI chips that are super, super dominant in this space. Our research is really what comes next. And our research in how do we build those, and we expect you to join us, or hope you'll join us in that revolution. So what is the future going to look like? First, software is everywhere, and Moore's law is ending, and various forms of software, data analytics, and AI is revolutionizing many industries like healthcare, autonomous machines, IoT, financial, retail industry, and so on. In addition, quantum computing is coming bit by qubit somewhere near you very, very soon. So 10,000 feet, that's kind of the underbelly of hardware that is happening. And so why computer architecture at Wisconsin? A couple of reasons. First, we have a very strong history, as I was just mentioning. Many techniques of modern processors like branch prediction, pipelining, chip multiprocessors, and so on were invented here. And we've had a very, very rich history in building simulation tools and making them open source that have been used by the entire community. Also, very strong presence of the things we look at, coherence protocols, consistency, GPUs, and so on. Several of our students and the faculty here have won many of the biggest awards in computer architecture, approximately 20 to 25 graduate students, and several well-funded projects that I'll talk about in a moment. Second, our graduate students have been prospering over the few years in many places, over a dozen in academia, including places like Illinois, Texas, Michigan, and UCLA, so on. As assistant professors, they've gone on to build really impressive research careers, winning the prestigious Sloan Fellowship, Career Awards, and the Morris Wills Award. Several are in very important industrial positions in companies like AMD, Cavium, Google, and so on. And we have a very strong future ahead of us. In the past 3 years, we've had 20+ papers in the top architecture venues. And my goal with this talk is to convince you to come here. We want to add you to this slide. So I'll spend the next few minutes talking about a couple of our research projects. And we have the Architecture Open House, in which you can talk to the graduate students to learn more about these things. Swami Tanu leads the Quantum and Emerging Systems group. His work is kind of in 2 pieces. One, compilers for quantum computers, and he's also working on cryogenic and quantum architectures. I lead the vertical research group, where we are focused on technology-driven architecture. Current thing I'm looking at is how do you break the programming wall for accelerators, in the sense of how do I take a deeply entrenched software stack that everybody's using and allow it to work with new computer hardware. In the past, I've looked at ideas of stream data flow and many others that you can see on my webpage, and happy to talk to you one-on-one as well. Professor Sohi leads the multiscalar research group. In the past, he's looked at speculative multithreading and variants of it. And recently, he's looking at non-traditional multi-core architectures, multi-core programming problems, and also looking at security. Mikko Lipasti leads the farm research group, where they've been looking at power efficient cache coherence protocols, on-chip interconnects, high ILP processors, and he's also been looking at some really intriguing work in non-von Neumann machines and biologically inspired computing systems. Mikko is an ECE, but CS students he has an adjunct appointment in CS, so he's somebody all of you can choose to work with as well. Matt Sinclair leads the HAL group, where he's been looking, his recent work has been on coherence, consistency, and data organization. He's at present looking at application design, and he's also looking at optimizing tools for hardware, software, and algorithms for emerging applications. Finally is Professor Joshua San Miguel. He leads the STACS research group, where they're looking at energy-centric computing systems. He's looking at approximate computing from circuits all the way to programming languages. He's also looking at energy harvesting and intermittent computing systems. So that's a quick summary of the architecture research group. So hope to have more time with all of you in the open house, and please feel free to reach out to me for any one-on-one discussions, and hope to see a substantial number of you here.
Karu's talk was a little shorter than what the schedule allowed. So I'm wondering, Alice, if you'd like to go ahead and start your talk. Good morning.
Good morning. Yeah, I'm happy to go ahead, if that's okay. Yeah.
That's great.
Cool. All right, so let me share the PowerPoint. I'm guessing you see my screen?
Yes, we have your screen up.
Awesome. Yeah, so thank you for coming today. So I'll be telling you about the MAD-PL group, which I'm a part of. And as you can see, our groups have MAD at the beginning, and most things in Madison do. So, of course, we all know software is everywhere. You're on a laptop right now or on a desktop. You're connected to the internet, to many other computers. You have tons of devices at home connected to each other, your phone, your fridge, your thermostat, etc. You're using some very, very complex software stacks, and the kinds of software that is running is affecting everything in your world, your healthcare, your money, and so on. So that means that there's so many people out there, millions and millions of people, and the numbers are growing, who are writing code. They're called developers, data scientists, software engineers, whatever you want to call them, right? So they're using tools to build this software and to reason about it. So the goal of the MAD-PL group has been to build tools that help programmers write software faster, better, more robust, more secure, etc. So I'm going to tell you about some of these things that we've been doing. And the goal is to, of course, avoid the huge problems that can arise through debugging. So this is, a relatively old study where they showed that, billions and billions of dollars are spent on debugging. And, these days, 312 billion can be just lost in a minute in cryptocurrencies. This is, again, an older study. These days, everything is running on the cloud, and we've seen, recent kind of problems with Amazon's cloud, Facebook's infrastructure that take out whole swaths of the internet due to silly bugs in the code. Additionally, people have been very concerned about code that is affecting people's lives. For example, in the United States, courtrooms have been using predictive software that detects whether you are going to recommit a crime and whether to allow you to go out on bail, etc. So there are big issues that can be caused through software that can affect people's lives. So the question is, what should we do, right? And that's where our group focuses its effort. I am Aus. The other faculty in the MAD-PL group are Loris D'Antoni, Somesh Jha, and Tom Reps. So we've been working at this problem from many different angles. And if you look at csrankings.org, which looks at the numbers of papers people publish in top conferences over the past 8 years, which is the period that all of us have been active, we are the top ahead of CMU and MIT in programming languages and logic. Logic means here formal methods. So the kinds of things that we study are verification, meaning proving that programs are good. They don't have unintended behavior like stealing your personal information, or perhaps crashing or taking down the internet, etc. Okay. Repair, which is the problem of making sure that a program that is broken automatically fixes itself, okay, which is a very interesting problem because people spend most of their time debugging. So if we can make that process automatic, that's a great productivity win. Similarly, we want to be able to generate code automatically. Indeed, that's the holy grail, right? Like, can we just automatically generate code? Do people have to write it? They can just say, I want a piece of code that does blah, 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 and code is automatically generated. So we've been working on all three facets of those problems. So let me just dig deeper into those and give you examples of what we've been doing. So what is verification? So verification, you have a program written in some language perhaps, or maybe even pseudocode, and a specification, which is a statement of what the program should do. So this could be something like, the program should not steal my private information, it should not crash, it should terminate, it should not have any memory leaks, etc. And the goal of program verification is to generate a proof that is, categorically, this program will never behave in a bad way according to the specification. Or alternatively, it could discover a bug. Okay, so this is unlike testing where you can only discover bugs. This is also constructing proofs, and these are mathematical proofs. So to give you an example, for instance, Tom Reps has been working on the problem of computational complexity verification, where you have a piece of code and you want to prove that its complexity is, for example, O(n) log n. Okay, and this is an interesting problem because if your code can exhibit executions that take a very long time, then potentially attackers can use denial of service attacks to take down your entire system. Okay. And Tom has been using some very modern and advanced techniques that relate to standard Newtonian analysis that you've probably learned in your numerical analysis course or machine learning course, but applying it to these complex things that are programs. Similarly, Loris D'Antoni and myself have been working on the problem of algorithmic fairness. So these are programs that are making predictions that impact people's lives. Okay. So for instance, imagine that you have a neural network that decides whether you get a bank loan or not. Of course, that decision can have a great impact on the trajectory of your financial well-being and your life in general. Okay. And our goal, for example, is to show that this outcome is fair for some definition of fair. Okay. And our tools will be able to prove such properties. Okay. So we've been working on proving, for example, that the algorithm is fair with respect to gender. Okay. Similarly, we've been working on neural network verification more generally. So I've been doing work in that space. Soumya has been doing work in that space, and Loris as well. Okay. So here the idea is that you have a neural network and you want to prove something about its behavior. And typically neural networks are these fuzzy things, like, they might see you in the picture, they may not see you. They may read a sentence and they may understand it or they may not. And one of the interesting things that we observe, and the community has observed generally, is that these networks are not robust. For example, you can take a sentence and then make a small spelling mistake in it, and anyone will still understand the sentence, but the neural network will lose it completely and won't understand it. Okay, so we want to prove that these neural networks are robust. And the reason for proving robustness is both security guarantees, because people can start fooling the neural network in various ways. And in addition, it's a way for us to get closer to something that we can call intelligence, because any definition of intelligence will imply that the agent is robust to changes in the environment or changes in the input. So for instance, here are some examples where we take the sentence, "This house is nice," and the neural network says, "Oh, this is a positive sentence." However, you change the house with a small spelling mistakes, and the net thinks it's a negative sentence. Similarly, if you say add a spelling mistake and change a word to a synonym, it might also change its opinion of the sentence, which is something that you don't want to happen. So this is a kind of an overview of some of the verification work that we've been doing. And there's another set of projects that are brewing and haven't yet seen, haven't been publicized, but we're happy to talk to you about them in our one-on-ones. So the next question is, what is synthesis? So verification is taking a program and proving something about it. Synthesis is more ambitious in the sense that I want to say something about what I want, to specify what the program should do, and automatically generate code that meets the specification. Okay, or just tell you that actually your specification is bogus. There is no program that can be written to realize it. Okay. And of course, we want to do this automatically. So the idea here is to make programmers more productive, specifically when they're building something complex that it's hard to reason about. So to give you some example, if you think of the cloud computing and data centers, you can think of them as these gigantic interconnected computers. So one big computer with so many processes and threads organized in a gigantic data center. So a lot of people spend a lot of time writing code to manage these data centers, and they can get things wrong. And if they get things wrong, bad things happen, like entire pieces of the internet can go down, as we've seen, for example, with the Facebook fiasco from a few weeks ago, and a bunch of Amazon outages in late December. So Loris has been working on this problem where you say what your policy is, and you specify what the likely failure scenarios are, and configurations for the network are automatically generated, so that network operators don't have to write them by hand and reason about them. And this can handle large data centers with more than 150 nodes, and even more than that these days, and has been applied to data centers in Microsoft Azure, which, if you don't know, it's the second largest cloud provider in the world. Similarly, we've been applying program synthesis to remove bias in programs. So the idea is that here you have a bias program that is perhaps unfair to some people versus others. And we want to take it and improve it such that we remove this bias. Okay. And we want to do that automatically. So this is also a notion of program synthesis or program repair. Okay. And the way we do that is using a combination of logical reasoning from the programming languages community and computational learning theory from the machine learning and statistical reasoning community. So there's a lot of these projects at the intersection of both programming languages, logic, and other areas, which make for exciting avenues for discovery. Another interesting project in the program synthesis arena is software deep-loading. So if you're building these days, say, a web app, you're probably going to be using a lot of packages, for example, on NPM or Node.js or whatever language you're building. And these packages are written by so many different people, and you don't trust them fully. And even if you trust them, these packages could be very large, and they have so many different components that you don't need the entire software stack that comes with them. Okay? And the bigger the software, the more likely an attacker can attack it. Okay? People talk about attack surface, so you just have a larger attack surface. So if you have such a project and you're really interested in a small piece of functionality, can you de-bloat the gigantic piece of software that you built into something that is compact and therefore reduce the attack surface? Okay. So this is both a program synthesis and a compilation problem, with the goal of making your program smaller and less susceptible to attacks. In addition, we've been, particularly Loris and Tom, have been looking at the program synthesis question from a foundational perspective. What does it mean to do program synthesis? And they've been building a framework that unifies many existing ideas from the literature. And the idea is here to take, a space of programs and a specification and produce programs that are good with respect to the specification. For example, you want to produce the fastest program that performs a certain task, that it can do matrix multiplication, for instance, instead of writing it by hand. So they've been building a foundational framework that can be used for many different applications. So to conclude, software is pervasive, as we all know, and it keeps changing, and it's very interconnected. And the MATPL group here has been working on 3 different facets. One is verification, proving that programs do what they're supposed to do. One is repair, fixing programs automatically, and then synthesis, which is generating programs so that developers don't have to do that themselves. So thanks again for coming, and I hope to see you here next year.
So we're running a little bit ahead of schedule. If Rahul is here and would like to start, let me know, and you can go ahead, and we'll just have a bit longer break.
Okay. Yeah, I think I'm ready, and I can start sharing my screen. All right. I hope you can see the screen.
Yes.
Great. Thank you. All right. Good morning, good afternoon, good evening, wherever you are in the world. It's too bad that you cannot come here, but hopefully we'll be meeting you all soon, or at least some of you soon. So I'm Rahul Chatterjee. I am a professor in the security group, and I'll be talking about the cool research we are doing in security and privacy in Wisconsin. And we will have an open house at 1 to 2 p.m. and feel free to ask more questions then. Oops, sorry. Yeah. I was previously talked about that our whole world is now surrounded by software and technology, and basically our critical infrastructures kind of rely on these things, starting from power grid to all the smart home, car. Even if it's not a self-driving car, even our cars have lots of software inside it. The industry relies on software and technology. And therefore, it's very important to make sure that this software and technology runs properly, even in the presence of adversaries. So that's what we do as security researchers, is basically understanding the threat that an adversary can cause and try to improve the state of the art so that we can safely operate even in the presence of adversaries. So I will start with a very obvious example. You might have seen it in the past. Machine learning is basically reshaping the whole world. And we are using machine learning for many different tasks. Right now, machine learning has better performance than humans in some tasks, like identifying objects and faces, and it can solve captchas, and it can even help doctors identify cancers on images on images. Now that is all great, and we want to reach and want to get those benefits of machine learning, but there is a problem that these are all assuming the whole world is there are only good people in the world. So what can go wrong if there are few people who wants to compromise? Well, they can create something we call adversarial example. So on the left, what you're seeing, that's just normal picture of a cat, and the machine learning classifier that I was talking about, one of those classifiers, can actually correctly classify it as tabby cat with a very high confidence. But one can create an imperceptible, very small perturbation and create an image that to a human looks like a cat on the right, but a machine learning classifier thinks it's a guacamole. So this is called adversarial examples, where you can add imperceptible perturbation to some to an image or a voice, and the classifier will completely misclassify it. So this is an example of image, but we have shown that this is possible to create adversarial examples in various digital form of the data, like malware classification. You can create a malware by altering some small part of the code so that the malware still preserves the maliciousness, but it will be misclassified by any antivirus or any malware classification algorithm. The same thing has been shown for spam, voice recognition, and even medical diagnosis can misclassify things. So, you know, as I just told, going back to the idea that, okay, machine learning is one of those digital technologies that are gonna, again, help us change, and will be used, are being used in very many safety critical systems, like smart cars, smart trucks, industries, and many more. I mean, this is just a small example of what machine learning can do. And that is great, and we want to take advantage of those technology, but we have to also make sure that we understand the risk and what risk associated with it, and how do you make sure that they're safe and secure. So this is just an example, but what I'm trying to get at is like what we do as a security researchers is take a perspective of how things can be broken, and by understanding that proactively, we try to make things safe and secure. Well, that's the high-level goal of the security, and that is why we are kind of a cross-cutting field that you might like any area in computer science and still work on computer security. It intersects, I gave an example of machine learning, and throughout this talk, I'll say how it intersects with many other fields. So broadly, the security research group at Madison is very diverse, and it's working with many different types of problems in the area, starting with trustworthy machine learning, that works on user authentication, cyber physical systems, security, and even human factors in computer security, because humans are the primary user of all those systems. And it makes no sense if your system is secure, but the user who is using it cannot use it securely. So I'll give you just a few sneak peek and teaser of the research that we do. And I'll be more than happy to answer questions during later. So one area that we started with machine learning. So machine learning in the area, what we are trying to understand is how are machine learning classifiers right now limited in their understanding of the objects. So what we call as intelligence, or their ability to understand the real world, is actually very limited. And this is important to understand because then only we can build robust machine learning classifier. So one quick example of the recent work that we did, and it was published in CBPI, is you can change the light that is falling on an object and flicker the light at a very high frequency so that the camera that is normally uses, it reads an image row by row, will see very differently than what a human will see. So at the bottom, a human will see a cup, and it will be classified as mug normally in the normal situation. But if the adversary controls the light falling on that mug, then it can be classified as ping pong ball or something else. And it's I have a video of this. On the left, what camera is seeing, and on the right, a human is seeing. So human is not completely oblivious to an attack that is going on. But if you have, say, some kind of robot or some other camera that is trying to detect an object, we'll see it very differently. So this is the case. We basically only control the camera and nothing else, and we show the attack. A little bit stronger threat model is when the attacker does not even. So previously we assumed the attacker knows the exact model being used by the camera. All right. And the other setting is where you don't assume anything about the model. You don't know what's the model. That's a complete black box. And can we still do the attack? So this is a situation, say, you bought a Tesla, and Tesla has some kind of model for detecting objects like the stop sign. You don't necessarily know the model, but can we still fool the model in detecting something? And I think Erland Somes is working on this area, and they have shown that yes. So there is also another, I have a cool video about that. On the right, it's a normal stop sign, and you can see the classifier is correctly predicting a stop. And on the left, it's the slightly modified stop sign. So they call artistic stop sign by adding some small tag on top of the stop sign, and it's consistently the car is predicting as speed limit 30 kilometers per hour. So yeah. Besides machine learning, there's another area that we are working on is how do you make sure the Internet of Things is secure. So primarily, Erland and I are looking into the way Internet of Things talk to each other is through right now is a third-party services called Trigger Action Platform, or TAP for short. And the TAP, so for example, you can have a rule something like, oh, if you're away from home, then lock the door. Or if you're close to the home, then unlock the door. So right now, all those information of location, lock, unlock information is being sent through these clouds in plain text. And cloud services like IFT and Zapier or Microsoft Flow is learning all those information, what you are doing, where you are, although they are not supposed to know any of these things. So we are trying to understand how can we minimize the amount of information exposure to this cloud. So that will provide privacy and security of the whole system. Talking about privacy, Kasim and Jay is working on, Jay Zhu and Kasim Fawaz working on these various ways to define improving the privacy of users. So they have a product, for example, you have a smart home device, smart speaker in the home, and how do you prevent the smart speaker from listening to you? And you don't want to trust Google when you decide. One option is take out the whole power plug from the smart speaker, but that's not very convenient. So they found out this convenient way of actually jamming the signal that smart speaker can listen to. So similarly, Kasim also has this work on understanding the GDPR, so that General Data Protection resources from Europe, which was published, I guess, in 2018, 17. So they are looking at how GDPR has actually changed the whole web, and are they actually following GDPR regulations? Are they following, ensuring that the user, has it improved user privacy? We're also looking into how can we actually have improve authentication systems. That's one of the key primary doorway to the digital world. And if our authentication systems are broken, then again, the same problem as like making things secure is not going to prevent, that's not going to be sufficient. So we have, I have looked into how to create, say right now the authentication systems are reliant on typos, passwords, and how do you allow user to log in with typo? Or what's the risk of your passwords leaked from one website on your other website? Like we are also looking into like, can we even differentiate a user from an attacker by looking into their typos? Kasim has this very cool work on can we actually detect a user by creating a vibration-based fingerprint of their hand. We are also looking into the authentication for the futuristic devices that are, so computing devices are changing in their forms and factor. It's no longer a laptop or desktop, or recently it's mobile phone. It will gonna be changed in next few years to something like augmented and virtual reality glasses, smart glasses. Computings are being used everywhere, like a smart door lock. And you have to constantly authenticate to those devices so that you can access the sensitive data that you have. Right? You need to authenticate to a door lock so that you can enter the house, or you need to authenticate to a smart glass or a smart attire so that you can take the advantage of your personal data through that smart technology. And we are looking into how do we actually improve the authentication, make it more usable and secure. I'm also very interested in looking into how technology is abused against vulnerable population, for example, people who are subject to domestic or intimate partner violence. For example, right now we have lots of applications that are, sometimes they're not even designed for spying, but can have all the capability of spying on others. For example, you have SMS syncing applications between two devices. And nothing is preventing an abuser from using that application to spy on their spouse or partner. Now, this is already a problem, and it allows like spying on someone through digital means. But recently, the proliferation of IoT or smart home devices actually makes the abuse even more dangerous, because now not only someone can digitally harm the person, but they can also physically harm, like locking out the victim from entering the house or changing the temperature. We have seen several reports where the user actually intentionally changed the temperature to something very high or very low, and the victim cannot control anymore. So I'm looking into how can we create socio-technical solutions to combat digital abuse against a vulnerable population. So this is just a few of the research that we are doing. Our group is pretty diverse, as I just told. Like many people, we collaborate very frequently with all the professors in the department. And if you're interested in any part of the computer science, there is a way where you can also work on computer security. So I talked about some of our work. Besides Paul Burford works on network intrusion detection. Bart talked previously. Bart also worked on fuzzing. He actually invented fuzzing and software assurance. Tom Raps, who also in PL group, but also works on trust management and model checking security, and others. This is just a few names that I added, but we collaborate pretty frequently with other groups. In terms of teaching and courses in UW-Madison, we are still adding more courses. Right now, we have this plethora of courses of like cryptography, software security, for lower level software security and advanced level security and privacy. And also we have some topics course, which is very specific to say privacy or authentication as well. With this, I would like to finish. Please go and talk to students from 1 to 2. You can also check out our group page, madisp@cs.cs.wisc.edu. And Madison is a pretty good place to live. I mean, this is one of the randomly picked pictures of the campus. And as Remzi was talking about, we are between two lakes, and that makes it a very nice city to live. It's also, I think it's one of the best cities to live in the US so far, but I might be biased. So, all right, I'll stop and off to you, Angela.
Thanks, Rahul. And if I'm remembering right, did you get one of your degrees here?
Yes, I did. I did my master's here. So if you have any questions about student life in here, please feel free to ask me.
Thanks. We're going to take a brief break and resume at 10 o'clock. So if you all could, I guess, let yourselves out, take a break and come back at 10 for the rest of the talks. We'll see you then.
Angela, should I go ahead and start?
Hey, why don't you give us 1 second? I'm trying to do some things on the back end here.
Okay, no problem.
Hey, Angela, you should be able to unmute yourself again.
So, Cindy, what do you think? It looks like most people that are going to join back have joined in at this point.
Absolutely. I will go ahead and restart the recording.
Okay.
We are recording. So whenever you all are ready.
All right, so I will start. Hello, everyone. First, I want to congratulate all of you for getting an offer from UW-Madison. So I'm an assistant professor. My name is Xiangyao Yu. I'm going to introduce the database group at UW-Madison. It's also known as the Wisconsin database group. Okay, so the database group has a really long history of success. So the modern database research started in 1970 when Edgercott developed this relational data model. And soon after that, in 1976, Professor David DeWitt started the database group in Wisconsin. So at this time, this was really early stage because at this time, this is one of the first database groups started in the entire country. And back then, the database was not even considered a independent research area, right? So, but even back then, the database group started to exist. Okay, and then over the last five decades, there has been many successful researchers coming out of the group. And most of these people are still active today, and technology leaders in both academia and industry. Okay, so we also see a long history of student success in the DB group. So some of the PhD graduates from our group went to become professors in really top universities like Berkeley, CMU, Cornell, EPFL, etc. And also many students went to top industry companies like Microsoft, Google, Oracle, Amazon, like all the top companies. Okay, so today in UW-Madison database group, we have 4 professors, An-Hai Dong, Paris Kutris, Jignesh Patel, and myself, Xiangyao Yu. And besides that, we also have several affiliates who are closely connected to the department and to our group, but are not faculty members in the group. And furthermore, we also have 30 plus students in the group. So the database group is one of the biggest group in the department with many professors and students. Okay, so for so in terms of research, because we have a lot of people working in the group, we work on all aspects of data management, all the way from raw data to getting insights from the data. So we work on things like data cleaning, transaction processing, data analytics, data science, and the theoretical aspect of databases, like data markets, and also the recently trending machine learning and artificial intelligence. Right. So for the next few slides, I will talk about the research done by individual like faculty members in the group. Okay, so I will first talk about the research done in Professor An-Hai Dong's group. An-Hai is focusing on building systems for data integration and data science. So for example, one particularly important problem here is called entity matching, where you may have, like in this slide shows one concrete example where you have 2 tables, and each table have records of some, like maybe users of a certain service. And the 2 tables will store the data in different formats. But sometimes the entries in both tables may be referring to the same real world entity. Right? For example, here in the first table, we have Dave Smith with his phone number, city and state. And in the second table, we also have David Smith, but the name is represented slightly differently. It becomes David D. Smith, and the phone number is also slightly different because we don't have the area code now. Okay, but if you look at these 2 records, you can realize it's very likely that they're referring to the same real world entity. Like it should be the same person. But now the question is, how can you develop a system that can automatically identify records that are likely to be referring to the same real world entity? Okay? And this is a very important problem that many companies care about. And Anhai builds systems that can achieve this using both traditional methods and also machine learning based methods. And actually, Anhai's technology has led to a startup called Green Bay Technology. And in recent years, this company has been acquired by Informatica. Okay, so next I want to talk about the research in Professor Jignesh Patel's group. I will talk about two projects. Like there are many projects in the group, but I will just highlight two. The first one is to build a data processing platform to perform data analytics at bare metal speed, right? So if you look at a lot of databases today, they work on a specific hardware platform, presumably of CPUs, but it's actually a big challenge to claim that you are fully leveraging the hardware potential. Sometimes the code works, but it's not fully leveraging all the available hardware resources, right? For example, maybe you're not saturating your storage bandwidth, and that's a sign saying you can further improve your system to improve performance. So the Jignesh prototype systems that can achieve this goal, they are leveraging both existing hardware, like modern CPU, and they are also looking into emerging hardware, like the new type of accelerators that are developed by computer architects, and figure out a way to use that kind of new hardware to run database and achieve the maximum performance. Right. And the second project, which is also it's a super cool project that is in Jignesh group, is called Data Chat. So what happens here is conventionally, when you interact with a database, you will write code like SQL. Right? Many of you have probably learned SQL in your previous experience. So SQL is not that easy to use sometimes, especially if you have maybe a complex query. So what Data Chat enables is conversational intelligence. So with Data Chat, what you are going to do is you just express what you want using a conversation. You can just talk to this artificial intelligence and just using natural language to say what you want to achieve. And then that the artificial intelligence will help you generate the code and make plots, for example, right? So this can be really convenient for people who are not experts in SQL. And this can also make it faster for you to explore the data. Okay, and then Professor Perez-Kutris is working on the theoretical foundation of data management. So for example, modern databases are getting more and more heterogeneous and also distributed. And that means you may have a lot of nodes and each one may have different computation capability and they are connected using different topology, right? It can be a tree topology, a mesh topology, or a complex graph, arbitrarily complex, right? So, and if you want to maximize the performance of your database, it is important that you design an algorithm or query optimization strategies that are aware of the underlying topology of hardware. And that is the first research topic that Paris is working on. And then another interesting topic is data market. So today, data is becoming a commodity that you can sell and buy on the web. It's just like today you can sell and buy like phone apps from Apple Store. Like that's become a really common thing, but it's becoming more and more common that you can also buy and sell data. And now it becomes a really interesting question in terms of how to price your data. Like some data can be more valuable, some data can be less valuable, and some data are bigger and smaller, or maybe more sensitive, etc. So you need to consider all of these factors in deciding the price of your data. So that is a very important and emerging market that is drawing a lot of attention in the community. Okay, so finally about myself, I work on new hardware and cloud native databases. So in terms of cloud database, as many of you might know, modern databases are moving to the cloud. And there are many good reasons people want to do that, because cloud can offer potentially lower cost, simpler fault tolerance, like higher scalability and flexibility, right? For example, if you deploy a database by yourself, you need to buy hardware, and you have to buy a certain amount of hardware, like 4 machines. But in the cloud, you can allocate hardware, almost infinite hardware, arbitrarily, because cloud has like huge amount of hardware that will satisfy your need for sure, right? So, and cloud native database is not simply deploying a conventional database in the cloud environment, but it's actually more than that. A conventional database, typically a distributed conventional database, typically take the shared nothing architecture where we have servers connected by network. But in the cloud, more and more systems are using a storage disaggregation architecture, where the storage is decoupled from computation and is managed as a separate service. Right? So this brings a lot of new challenges and also opportunities in optimizing your database performance. So you may have heard of some systems that is already moving to the cloud, like Amazon has Aurora, has Redshift, Athena, and there is Snowflake, there is Foundation DB, etc. So many companies are already doing this, and this is becoming more and more important and interesting. Okay, so the second class of project we work on is about new hardware devices. And this is similar and related to what Jignesh is working on. Well, modern hardware is getting more heterogeneous, and a lot of hardware devices are very promising to accelerate data processing. For example, GPU have massive parallelism, and if you can do data analytics on GPU, then you can potentially get an order of magnitude speed up. Right? And we look at hardwares including GPU, SmartNIC, which performs some computation inside the network, and also non-volatile memory, which is sort of this cheap memory that can extend existing DRAM. Okay, so to summarize, the database group at Wisconsin covers, well, we do research in a lot of areas, ranging from the theory to hardware software development, data cleaning, and also data science with machine learning support. And finally, I want to emphasize that there is an open house later this afternoon at 5:30 to 6:30 p.m. Central Time. So please join and talk to our students. All right, that's all I have. Thank you very much. And I hope to see you in person later this year.
Thank you.
Angela, can I get started?
Yes, it's all yours.
Good morning, everyone. My name is Ming Liu, who studies computing networking. I'm assistant professor in the networking group. So firstly, congratulations on your admission, and we are very excited at the potential of having you join us. In today's talk, I'm going to talk about two things. One is give an overview about some of the projects that we've been pursuing at UW-Madison, and also briefly talk about networking research in general. So the major goal of networking research is to build fast, efficient, secure, and reliable networking systems and protocols at different scale. In terms of fast, we are trying to achieve the physical limit of the underlying communication of the communication medium for various traffic profiles. We are not only looking at latency, but also high bandwidth for competing networking streams. So here, efficiency means energy efficiency, like bandwidth per joule, or cost efficiency, bandwidth per dollar. For example, one of the questions that we have been asking from our community is like, how can we build a cost-effective networking infrastructure for one kind of applications, such as CDN or video streaming. But more importantly, we need to consider efficiency in multi-tenancy settings. So in terms of security, our goal here is to minimize the attacking vectors from the networking perspective, but also invent fast attack detection and prevention mechanisms. Regarding reliability, we are trying to build systems that can maximize the mean time between failures and minimize the downtime. But we also want to develop tools for prompt troubleshooting to localize a fault. So the networking research will touch a range of skills. So the internet is the prominent presence that connects an ever-growing number of networking systems, devices, and people across the world. An additional impact is that the connectivity that we enjoy from wireless that enable mobility, which kind of connecting devices which cannot be connected in the wired case. Over the last 15 years, we have seen the concept of internet as well as wireless network has migrated to dynamic data centers, which has powers a number of applications that we have been used in a day-to-day basis. So of course, like currently, the data center has become the major source that generates traffic traverse the internet. So in addition to these two networks, we're also interested in SoC interconnects as well as cluster interconnects. Overall, the networking research is driven by three factors. So the first factor is new applications. So essentially here, there are two views. One is like we want to build new networking systems to enable applications. For example, we have this living IoTs, the embodied networks. Another aspect is that for given applications, how can we build efficient network infrastructure for some applications like serverless functions, blockchains, or ML applications? So the second driving factor here is new hardware. So this is not only including new networking fabric and devices, but also new hardware from compute and storage. So for example, one area that I will be working on is called program networks, where people put some of the compute on the traditional networking hardware so that you can enable flexible and stateful computations for each individual packet. So as a result, you can use this to improve the transport protocol as well as distributed applications. So for some of the compute and storage devices like energy harvesting platforms or computation SSDs, we also think about how can we effectively connect them together for applications. So the last driving factor here is new experience, especially new operational experience. So by a detailed instrument of the networking systems, we can do comprehensive characterizations and then apply analytic techniques to gather insights. Such kind of insights will help us to enhance existing networking systems as well as to improve or like giving the guidelines for next generation networking system design. So in order to achieve this, you will need some great toolbox where you will borrow some of the techniques from other fields like programming language, algorithms, MLs. So for example, one important topic in the area is called networking verification, where people trying to encode packets of flow on networking states into constraints and using SMT solvers, like set solvers, to identify some of the counter cases. Next, I will talk about the networking research at UW-Madison here. So the networking group here have three faculties. So Professor Paul Bufford has working on internet management, security data science. Professor Shun Banerjee is working on wireless mobile systems and edge computing. And I'm working on rack scale and cluster scale networks with a focus on networking-based hardware accelerations. So one of the problems that Professor Paul Bufford as well as his group trying to solve is how to improve performance for computing networkings. So of course, performance itself is not so interesting because performance without resonance is not so useful. So one way to better define the scope that his group has been working on is by the techniques and approaches that tend to be extremely empirical and experimental. So a lot of work has revolving around you want to develop techniques to gather data from the internet, and then apply a wide variety of techniques to analyze the data, and then gather insights, and using the insights to build and test existing systems or even deploying new services in the internet. So for example, one project that his group has been working on is called Accessing the Internet Risk, which has a focus, like a kind of impact on the society. This is given the trend of climate change. To get a flavor of what his project is about, there are two questions that his group trying to answer recently. So one is like, given the climate change, the cost sea level rise, as a result, what is the impact of the buried cables? So his group has been working on a project called Project Atlas, which is building network connectivity for the US and for the world. Given the capability, they are able to identify for the buried cables, how many of them will be go underwater in 100 years. And given such cases, how can we serve such buried cables undersea? So another problem that the group has been examined is like, what is the impact of the wildfires for cellular tower infrastructure? So probably you have heard about wildfires frequently. So what they found is like, there indeed a lot of cellular towers has been impacted by wildfires, and they are able to assess the threat levels and then identify the threat areas and also propose techniques to enhance the threatened area cellular infrastructures to avoid such risks. So many of these works has gained significant attention from the public media and press. So another project that his group has been working on is called Internet Vibration Sensing, which is a little bit obvious. So ground motion and structural monitoring is critical for public safety and security. The approach that they have been working on is called investigating the opportunistic vibration measurement from the computing and the communication infrastructures. The hypothesis of the project is trying to see whether they can detect vibrations using internet. And a very intriguing result that they found is like some of the cables and as well as the buried internet consoles is able to detect such vibrations. So this is similar as a YouTube video where people like some guy shouting at the disks in the data centers and measure the read and write latency. And what they found is like the latency actually increase when you're shouting at the disk. There are other two projects that he has been working on. I will not go into details. You can talk to him in one-on-one. One is regarding mapping internet connectivity. Another one is about measurement and analysis of the internet traffic protocols and systems. Next, I will introduce our expert on mobile and wireless network, Professor Shuman Banerjee. So over the past years, Professor Shuman Banerjee, as well as his group, has built significant infrastructures in the building and on the campus to enable empirical research. So for example, his group right now is able to operate their own 5G networks in campus. Now we have our own TV web space. We also deploy a significant amount of 802.11 based wireless stations in the campus. So recently, his group is also being able to deploy connectivity on the metro bus that carrying people between Madison and Chicago, and they also being able to explore the network connectivity in these kind of cases. A more recent project that they have been working on is to enable deploying the capabilities to mobile sensing and edge computing to tracking the automobiles when they're driving on the road. So they are, as a result, they're able to answer some basic questions regarding the driver experience and as well as characteristics. So the most interesting bit from the project is like what kind of data they can gathering from the tracking systems and what kind of insights they can extract from them. So another related project regarding mobile sensing and edge computing is mobile health care. So over the past, they have been built a framework called Parajob, which providing compute and storage capabilities for edge applications. And it also provides a very flexible interface for third-party applications developers. So for example, you can connect your wearable therapy trackers, getting data and using Parajob to getting data and then outsourcing the complex queries to the cloud. As a result, you are able to answer many complex questions. So there are two new directions that Professor Shuman Banerjee explored recently. One is satellite networking, another one is space IoT. The ideas here is trying to using networks of satellite to provide broadband network and connect low power devices to satellites for efficient communication. If you are interested, please reach out to him in your one-on-one for more details. And finally, I want to briefly talking about the work that I've been working on, which centers around rack-scale infrastructure disaggregations. Infrastructure disaggregations basically provides us three benefits. One is that elastic scaling, where we don't need provisioning. We can scale our resources based on application demand. The second benefit is consolidation. Essentially, by consolidating multiple devices on the same one, you can maximize the utilization. And this also providing the third benefit, which is cost savings. So driven by the availability of high bandwidth cluster interconnect, we have seen different kinds of disaggregations like compute, memory, storage, and even networking fabric. And for each of the domain, we also see a number of new hardwares come into the picture. For example, we have domain-specific accelerators, we have heterogeneous chiplets, we have persistent memory, open SSDs, joint named SSDs, and programmable switch networking adapters. And given such new hardwares, one of the most important problems that we try to answer is like, how can we build applications in such kind of infrastructure? A key problem that our group is trying to answer is like, what is the control plane and data plane when we design systems and applications under such disaggregate infrastructure? So there are three focus of my group. So one of the project we are pursuing is programmable storage disaggregation. So the idea here is that given the programmability on the storage data plane as well as the networking data plane, how can we take advantage of them to improve the storage applications to maximize efficiency under multi-tenancy settings? So the second project is called host assisted computing using programmable adapters. So these programmable adapters are SmartNICs, DPUs, or infrastructure processing units. So we want to use them for different ways. For example, we want to using such kind of SmartNICs for as IoT IO hubs to manage your host portfolio devices. We also want to use them as offloading engines where you can take some of the commands from host and run on these SmartNIC cards. We also sometimes want to use them just as a peer device, like a microservers, which stay on your PCIe bus. So the third focus of my group is on heterogeneous interconnects. So in addition to high bandwidth Ethernet, we want to looking forward to see what is the capabilities, limitations of CXL, these kind of heterogeneous interconnects, and how to use them for storage, memory, and compute disaggregation. So hopefully I have got you excited about our research at the networking group. So to wrap up, so we will have open house at 2 p.m. to 3 p.m. this afternoon, where students will present a couple of their projects, and we also want to answer your questions. And we also looking forward to meet you in our one-on-one today and tomorrow. That's all what I have. Looking forward to see you in Madison this coming fall. Thanks.
Thank you for your presentation. We are waiting for our next presenter to arrive. And while we wait, instead of switching up the schedule and further making some more confusion, I think what I'll do is I'll share my screen and we'll talk about the schedule. And Ming, can you turn off your camera? And I'm going to share my screen. Thanks. So I'm just going to go through what's happening. As I've mentioned, we actually have added some things maybe since the last time you checked carefully on the schedule. So you're in the faculty talks right now, and this afternoon there will be a lot of area open houses and also tomorrow. And if you look at the schedule, you can see security has their open house from 1 to 2, architecture from 1 to 3, systems is having 2 sessions, 1:30 to 3 today, and then an early morning session tomorrow. networking from 2 to 3, programming languages 3 to 5, robotics 3 to 5, database 5:30 to 6:30. Tonight, I hope that many of you will be wide awake and able to join us. I will be doing a question and answer session, and this is going to be a pretty open session where any questions you have about our program, about admissions, about the timeline, about Madison, etc., we're open to pretty much any questions. And that will be from 6:30 to 7:30 this evening. So I really hope that some of you, or most of you, as many of you as possible, will be able to join us this evening. That won't be recorded, but I hope to compile a Q&A, questions and answers, that we can put on the website for people that have to miss that. Okay, tomorrow is the day that students, you can hear the student voice. So tomorrow there will be more faculty meetings, but there'll also be a few research area open houses, one from 8 to 8:45 for systems. Visualization will have an open house from 10 to 12 p.m. and HCI from 10 to 12 p.m. There is some overlap with existing activities in those open houses and possibly some faculty meetings, but try to maximize your participation if you can. SACM will be having, that's the student ACM group, will be having their session at 9 a.m. and that is going to be a great time to get to hear about our students and their perspectives on what it's like to be in Madison, study in Madison. They can also give some tips about, finding research areas of interest and finding faculty to work with. So highly recommend, if you're able to be awake at that time, going to the SACM session tomorrow morning. And for those of you who registered for the WACM, the Women's ACM meeting, they should have sent you a link to, we gave them the list of registrants, and they should have sent you the meeting link for the WACM meeting, which is at 10. So that's the schedule, and Cindy is
Yes. Yep.
here.
Our next
Great.
faculty
Okay.
member is here.
Awesome. So the next up is speaking for the theory group, Professor Jin-Yi Cai.
Hi, thank you.
Let me unshare my screen here.
Let's see, can I share screen?
Yeah, I'm going to stop sharing mine. There you go. Welcome, Jin-Yi.
Okay, thank you. Let me try. Okay, I think that's good. Can this be seen?
Yes, we can see your theoretical computer science.
Okay, wonderful.
UW.
Thank you for all. Okay, well, so this is I'm Jin-Yi Cai, and this is a presentation to the incoming graduate students, and we all know that to a successful department, graduate students is an indispensable part, and we truly welcome you all to our department. I think it's a vibrant, wonderful place to do concentrated research. And what I like to do is to spend 10-15 minutes to give you a flavor of our theory group. This is one of the research groups within the department. The group boundaries are not very sharp, but basically for the purpose of this presentation, I'm going to describe faculty who primarily work in theory. So what is theoretical computer science? Well, let's see, how can I go? I am sharing. Okay, I don't seem to be able to. Okay, did it show the what is theoretical computer science? Is it shown?
Yes.
Okay,
Yep, it moved
wonderful.
ahead.
Okay, so well, I trust that the incoming students, even if you're not primarily intended to be in theory, you probably have taken some theoretical computer science courses. The theory consists of, I think, in the most broad sense, two components. One is algorithms, one is complexity. It basically is the two sides of the same coin. Algorithms trying to find the most efficient algorithms for a particular problem at hand. And complexity tries to assess the inherent complexity, the algorithmic difficulty of solving a problem, and hopefully proving an exact bound as to where the problem really requires this amount of work. And it is really a most fundamental area, I would think, of computing. It asks the most basic questions of what tasks can be solved efficiently, what cannot, with just, you know, applications everywhere. Basically, it's the heart and soul of computing, I would say. Give you an example, and some of you probably familiar with. If you are talking about, say, searching or sorting, then of course, these problems can all be solved very efficiently. But there are problems where on the face of it, just looking at it, it may not be so obvious that there are efficient solutions. For example, matching, network flow, things that, a naive approach would seem to require exponential time. Exponential time means that the number of steps you take will grow exponentially in the size of the problem. And yet these problems like the matching and flow actually do have efficient algorithms. They require a deeper insight into the problem space. And on the same time, there are various problems. From undergraduate courses, you're probably familiar with these NP-complete problems: satisfiability, Hamiltonianicity, coloring, vertex color, independent set. They all seem really require exponential time. And then they can be used as guarantees of security. For example, that you'd really had to do this amount of work to get the result. So these are all very basic concepts in theory and originated from theory. From historical roots, if you look at the entire subject of computing, it started off with the work of Alan Turing, Kurt Gödel, Alonzo Church, Emil Post. And you may or may not know that Stephen Kleene was one of the founding members of this department, who received the National Medal of Science, was one of the early contributors to the foundation of computing. And if you look at the highest award in computer science, it's called the Turing Award, a large number, some of the names you may have seen from undergraduate courses, some of them you may not, but they are all giants in the field, and they set at the foundation, sort of set what is computer science a science instead of just a few bags of tricks. And I think it's probably the biggest group among areas of computer science who were recognized by the Turing Award. So this is an area that requires extraordinary contribution and has witnessed one of the most foundational advances in every aspect of computing. So it's very integral and fundamental to computer science. However, the subject is relatively more demanding. The most telltale or somewhat of a characteristic feature of theory is that the results, generally speaking, expected to be proved, so that presentations is sort of on the the value of the field, the metric of the field tend to be on things that are provable. Okay, so this I think is one of the more distinguishing features, if you will. Right now at Wisconsin, we have these 5 faculty members who are primarily working in theory. By the way, if anyone has any questions, I think I could try to answer questions in the chat box, but in the meanwhile, I will continue. So I will briefly describe some of the work of these faculty members. And I have put their websites there. If you have a chance, you can copy down. And maybe these slides I can share with our friendly staff who are always so supportive. And you can write them down. Of course, you can also just directly go onto our department page and look for. So we have about 15 graduate students. The PhD recent graduates work in academia or in industry labs, including Google Research, Microsoft, IBM, and postdocs and faculty at various universities that you can see in this list. So let me give 1 minute per each of the faculty that I have listed here. For Professor Eric Bach, his main research area is in algorithms that connected with number theoretical algorithms, algebraic algorithms, combinatorics. The number theoretic algorithms are particularly useful in cryptographic applications. He uses analytic techniques that usually comes from the branch of analytic number theory, as well as algebraic geometric methods. These have applications in cryptography, pseudorandom generators, and quantum computing. So some of the notable accomplishments by Professor Eric Bach, for example, various results in computational number theory was based on the assumption that the what's called the extended Riemann hypothesis is true. There are certain ways that you can bypass them, but sometimes you can show that under the hypothesis of the extended Riemann hypothesis, this algorithm definitely works within that amount of time. So in some sense, if your algorithm actually failed, you'll probably become even more famous because you have disproved the Riemann hypothesis, the extended Riemann hypothesis. Okay. So there are works on factoring numbers with a prescribed set of prime factors and so on. Anyway, so let me summarize by saying that Professor Eric Bach's work is concentrated on in the area that has to do with algebra, number theory, and its application to computer science. Next is me. I will be very brief. I have worked in computing for, let's see, 35 years or so. I have worked on various different things. You can check on my DPLP page to see my publications. In the last 15 years or so, I have primarily worked on the classification theory of counting problems. And they come in, say, constraint satisfaction problems called a CSP. These are classifications for every problem in a full class into either solvable or difficult. And you can imagine it's like a dictionary or like a periodic table trying to lay down all these things. Let's see why I'm going backwards. Okay, so with a former student, I had written a book. Okay, partially completed book. It's only volume 1. Volume 2 is yet to be completed or to be published, in which we summarize the work in this area And the work has been, not the book, but the work has been recognized by the Gödel Prize and the Fulkerson Prize. So this is some of the work that we have done, and this is the area that I have focused my research attention on in the last 15 years. Oh, I should say that I have an hour this afternoon between 2 and 3 that I would be happy to talk to any one of you who signed up or like to just hop in to chat. Professor Ilias Diakonikolas joined our department not too long ago. He has had very broad experience in many areas of computing, in particular learning theory and the foundations of machine learning. And this is one of the very hot areas. This connects with theoretical computer science and statistical questions. It talks about learning from noisy data with adversarially placed noisy data, not just the ordinary statistical noise model. Supervised learning, high dimensional statistics, information computation trade-off. And so some of the work is on non-parametric estimation and hypothesis testing. So these questions originally came from mathematical statistics. But when you add the constraint of how much computing that you are allowed to do, then some of the questions attain a very renewed life its own, because in classical statistics, the question primarily concerns with information theoretic bounds and information theoretical limits. Okay, so this is an area that has had a great deal of activity in theoretical computer science, in fact. The research work of Professor Dieter von Malkebeek is on de-randomization, connections with circuit lower bounds, polynomial identity testing, lower bounds for NP-hard problems and intermediate problems, kernelization compression. Some of the recent work, it's been highlighted here, says the systematic work on the power of pseudorandom generators for polynomial identity testing based on what's called the vanishing ideals. These are algebraic constructs in a polynomial ring. De-randomizing isolation lemma on space-bounded setting, and reductions between NP intermediate problems, in particular what's called the minimum circuit size problem, which one of the problems has generated a lot of, this problem called the minimum circuit size problem has generated quite a bit of attention. Actually, I myself have worked on this in one of the earliest papers with carbonets that was perhaps a little ahead of its time. For about 10, 15 years, there was no activity, and then there was a lot of work now recently. Professor Christos Zamos is again working related to computational learning theory and computational statistics, but he also has interest in mechanism design and algorithmic game theory. And I think it's one of the more recent interests that is fine-grained complexity. So for example, you can ask about how to improve machine learning algorithms to handle noisy and biased data. So that there could be, from the sample, it's not just white noise, but there could be systemic bias. Some proportion of the data is fed in adversarially and so on. Optimal selling mechanisms, that in mechanism design theory, if you have item by item type market, then a lot of theory has been very studied, very quite understood. But if the selling mechanism is a bucket, say for example, I can sell item 1, 2, 3 in one bucket, or 2, 3, 5 in another bucket, and how do you price the things in such a way that it elicits the best revenue, for example? These are very practical questions that people are actually really interested in, say, at various companies like Google. How to speed up algorithm performance. Okay, so this is some of the very quick wrap up of the area's faculty's research interest. I think I should stop here. I got on a little late because the computer science support staff wanted to talk a few things. So I think I'm just about 15 minutes. Okay. So any of you who are interested in talking to me are welcome to come talk to me at 2 to 3. Okay. Bye.
Thank you, Jin-Yi.
Thank you. So I'm going next. I hope you can all see my screen now.
Yes, we can see the screen.
Okay, perfect. So welcome everyone to the Welcome Week, and I hope you get to learn a lot about our department, and of course I hope you decide to join us. I am speaking on behalf of the optimization group here at UW-Madison. My name is Jelena Diakonikolas, and I am one of the assistant professors here in the computer science department. So what is optimization about? Well, you can pose almost anything as optimization. You either want to maximize some good stuff, such as some profit or reward, and there are usually some constraints in what you can do, or, and this can even be shown to be equivalent, you can try to minimize bad stuff, such as cost, again, subject to some constraints. Now, when you write things like this is super general, and many, many things out there can be expressed as optimization. You can even say that some natural processes are optimization, and in the area where I work, some people actually made a connection between optimization and the dynamics of slime molds, which comes from a natural process, to solve some problems that come up in machine learning. So there are some super interesting things out there. Your choice of a grad school is an optimization problem. How you pose it, that's up to you, but maybe you want to maximize your chance of success or minimize your chance of failure, subject to whatever constraints you have in terms of funding, how much you like the place, how good the fit the place is for you in terms of research advisors, and so on. Immediately, I have to alert you that just because we know how to pose something as an optimization problem, it does not necessarily mean that we know how to solve it. And in fact, there are many, many optimization problems out there that cannot be solved efficiently or at all. So this is a very, very broad research area with a lot of research activity. And as I already mentioned, nature is a prime optimizer. If you think about processes that happen in nature, that they are essentially perfect, and they will work as a perfectly optimized algorithm. And there are even some algorithms out there that are inspired by nature. Not many people perhaps work on it here at UW-Madison, but it does come up in research of myself and Professor Wright. And we sometimes do make use of this connection. If you think about data analysis or data science, well, you could say that's pretty much optimization, because what we do in data analysis is that we try to maximize maybe simplicity of explanation, subject to the model that we are forming having sufficient agreement with the data. And the guiding principle here in data analysis is what is known as Occam's razor. So if there are many different ways of explaining the behavior of the data, most likely the simplest one is the right one. On the other hand, we also use optimization a lot in modern data analysis. It is a fundamental tool. Much of data analysis or machine learning would not be possible without the use of specific optimization algorithms, such as stochastic gradient descent, methods with momentum, matrix optimization methods, coordinate descent algorithms, automatic differentiation or backpropagation that comes up in the training of deep neural nets and so on. And my senior colleague in the optimization group, Professor Steve Wright, co-authored a very recent book with Ben Recht that talks about these different optimization algorithms for data analysis. Of course, optimization comes up in many different areas of data analysis. One specific area where much of my research falls into is in supervised learning. And the setup of supervised learning is that we are given many different labeled data vectors, and the goal is, given an unlabeled network, unlabeled vector, we want to predict its label. And the setting here is that the data is huge, since this is happening within the machine learning setups. So we need really fast optimization algorithms. And this has been a very vibrant research area in the past years. If you want some examples, well, there are many that you can write this way. You can think about these data vectors representing the medical profile of a patient, and then a label would be a medical diagnosis. And things like that are already being used, at least to some extent. You can think of them corresponding to speech recognition, where you have recorded voice that is broken down into numerical representation, and then you want to assign it a label. What is the word that was recognized? And image classification, prediction of earthquakes, prediction of organic chemistry reaction, many different things. Some of the most basic inference tasks that come up in supervised learning are classification, where we have two possible labels. We can have more, but most basic example is we have two, where there is a positive and negative example, and we want to create a model that separates them. There are also regression tasks where labels can take many different values. Some of these problems can be, the problems of finding a right model that explains the data can be posed as convex optimization problems. And some standard examples are logistic regression, linear regression, loss of rich regression, and so on. So there is a space for developing fast convex optimization algorithms. Convex setting is usually the easier ones. Things are more controlled. There are, of course, many non-convex optimization problems that come up with, and the standard example is the training of deep neural nets, and there is still a lot of research activity there too. Much of my work is focused on working with gradient-based methods. So you can think of a gradient as being a slope of a function. And the basic intuition for how these methods work is as if you were trying to get down a foggy valley, and you stand at a certain place, you look down at your feet to see what the slope looks like, and then you decide how much you're going to move. And there is a trade-off in how much you should move. Right, if you move too much, you might completely miss the bottom of the valley. If you move too little, it might take you a long time to get to the bottom. So that's just the basic intuition. Of course, there is a much broader story of how to develop methods that are efficient. The optimization group is very heavily involved in data science activities at UW. Worth mention is the Institute for Foundations of Data Science. This institute is led by Professor Wright. It is funded by the NSF, and it has three core areas which are computer science, math, and statistics. About 25 faculty at UW-Madison are involved in this effort, and there are many postdocs and grad students. IFDS also provides some funding for research assistants at graduate level and so on. We also have partners at University of Washington, at UC Santa Cruz, and U Chicago. There is another data science effort at the Wisconsin Institute for Discoveries. If you were visiting us, you would see that across the street from the computer science building, there's this beautiful Wisconsin Institute for Discovery building, and they have a data science hub. This effort is led by Professor Ferris. So both of our senior faculty members are leading data science initiatives here at UW. Some of the research done here also has impact that goes beyond academia. In particular, Professor Ferris worked on the distribution of COVID-19 vaccines here in Wisconsin. And as you might remember, when vaccines were first developed, there were many constraints in what could be done because initially there was a limited supply. There were also constraints regarding how we store those vaccines. So it is a very, I would say, tricky optimization problem, especially because you had to worry about things like fairness of implementation, because they're socially vulnerable group, they're rural communities. So you needed to have a proper planning of how to distribute the vaccines. And Professor Ferris was actually working with the Department of Health Services and the National Guard, and his solution was implemented here in Wisconsin. This is the summary of our optimization group. Shown in red are the core faculty who are in the computer science department, and the rest are the faculty who are in other departments but are affiliated with computer science. Many of us you can find on the 4th floor of the Wisconsin Institute for Discovery. And there are also many other faculty who have interests in optimization, but are not part of the core optimization group, so are not listed here. So this is the Wisconsin Institute for Discovery, which is across the street from the CS building, and many of us also have offices there. So I'll give just a brief summary of the research of our core faculty. Professor Ferris, I have already mentioned some of his research. More generally, he works on many applied optimization problems, such as in energy systems, in environmental optimization, fish habitat, and so on. Professor Steve Wright also has a very broad research interest, mainly within nonlinear optimization algorithms, and he also cares a lot about applications in data science, machine learning, climate science, engineering, and so on. Myself, I work primarily on efficient optimization algorithms for data science. I also care a little bit about lower bounds, which is showing what is the best we can possibly hope for. So it just gives a certificate how well we can do. I am also interested in connections between optimization and dynamical systems, and also optimization that is used within game theory and equilibrium problem. Professor Yudong Chen, he recently joined UW-Madison. He will be presenting also on behalf of the machine learning group. So he's half and half between optimization and machine learning, and has interests that fall in both areas. Perhaps some problems that are relevant to optimization are sparse recovery, compressed sensing, robust matrix completion in PCA, and so on. There are also faculty from other departments working on core optimization problems, Jeff Linderoth and Jim Lutke, who both work on a mix of integer optimization and stochastic optimization, and some applications in energy systems, resource planning, and so on. Also from ISYE and ECE department, we have Alberto Del Pia and Rob Novak. So Alberto works on mixed integer, linear and polynomial optimization, combinatorial optimization, complexity, and feature selection in machine learning. Professor Rob Novak is in the ECE department, and he works on machine learning and optimization, information theory, and signal processing. We offer a number of classes here at UW-Madison. They're introductory core optimization classes. We have a number of classes at the graduate level. I often teach nonlinear optimization 1, which covers many of the algorithms that are used in machine learning. And there are also some related classes that do not fall squarely within optimization, but use some optimization, and they're frequently taught by our faculty. Just this semester, I'm teaching Foundations of Data Science class, which is a newly developed class, and you can learn more about our group at this link. So I think I'm at about 15 minutes, so please feel free to reach out with any questions, and I'll just stick around even here on Zoom in case you want to ask any questions on chat.
Thank you, Jelena.
Mm-hmm.
Right, Angela, shall I go ahead and start the robotics talk now?
Yes, you can. Go ahead and you're on. And there's a little break. I know you're speaking before and after, so we'll have a little break between this section and your next piece of talk. Okay?
Okay, sounds good. Can you see my slides?
Yes.
Let's see, are you seeing my navigator, or are you seeing the actual slides?
I see Wisconsin Robotics page.
Okay, cool. I'll just assume you all are seeing the right thing then. Okay, sorry, can you still see it? It's saying that my screen sharing is paused on my screen at least.
We're seeing your actual slide.
Okay, all right, cool. We'll just
I'll
assume
tell
it's
you if
working
it
now.
doesn't, I'll share if it doesn't advance when
Okay.
it appears it should.
Great, thank you. Okay, so hi, good morning. My name is Josiah Hanna. I'm an assistant professor in the department. I work at the intersection of robotics and machine learning. And so I'm gonna give a 15-minute overview of the research which is happening in robotics here. So if you're not, let's see. So if you're not familiar with robotics research, here's just kind of a quick definition of what goes on. But robotics is the field of computer science and engineering concerned with creating robots, or just devices that can move and react to sensory input. So not all of robotics is, like kind of traditional like mobile robots or robot arms, but can be any sort of like device which is in an environment and is able to take actions in response to sensory input. There's a number of robotics faculty, both in computer sciences and in other departments across campus. So here in computer sciences, the robotics faculty are Bilge Mutlu, Mike Gleischer, myself, and Mohit Gupta. Bilge and Mike work both in robotics as well as human-computer interaction in this area of human-robot interaction, as well as making like fundamental contributions to how we control robots. My own research sits at the intersection of robotics and AI, in particular machine learning, and within that reinforcement learning. How can we get robots to learn to accomplish, to take actions to accomplish their goals? And then finally, Mohit works at the intersection of robotics and computer vision. And so you'll hear more about Mohit's research later during the vision talk.
Were we supposed to be seeing a slide with your
You were,
pictures?
yes.
Okay, it did not advance.
Let me try something real quick. See if I have two monitors up. That might be the.
Now we can see the images, but we're seeing your the side images too.
Okay, great, thanks.
Now we have a machine learning presentation.
Oh, well, that's weird.
Oh, it seemed to have been the right one just a second ago. It was showing Bilge and the others, the faculty.
Right. So what, I'll just reshare just to make sure that robotics group. Okay.
We see the right thing now.
Okay, I don't know why it's telling me my screen sharing is paused though.
Do you want to, once you go back to full screen sharing, do you want to try to advance to make sure it advances for you?
Yeah, so this is a picture of the faculty, and then I just advanced, but I don't think it probably advanced.
It is not advancing.
Okay, well, I don't want to, let's see, I will just kind of go through this. I take it you can see my slides now, so I will just not go into presentation mode, just to, I'm not sure what else to try, so.
You need a robot.
You're right, yeah, should automate this task. Okay, so I'll just kind of continue. I think the slides can be, seen pretty well. Let me just make it a little bigger and then, okay. So weird, maybe I have too many keynotes open. Okay, so robotics in research in the department spans both physical robots. So, how do we get robots to actually take actions in the world and do, like, for instance, you have a robot which has a complex arm with maybe, some like, gripper on the end of that arm. How can we get it to manipulate objects? But then robots also, more increasingly, we want robots to be placed into environments where they can interact with people. And so this introduces new challenges besides just being able to take actions to affect the world, but also like understanding social context and understanding, how what the robot does is going to affect like the internal state of the people that it's interacting with. So I'm going to go through a number of examples of research which is happening in the department right now. And so I'm going to start with some work that Professors Bilge and Mike have done in collaboration. So in this case, we're looking at, how can a person control a robot? So what we want to see is that when the person moves their hands, that they're able to control a robot in a very natural way. But there's a fundamental difference in how the robot moves and the person moves. They have very different arms, but we still need to kind of want to capture the same motion so that a person can control the robot in an intuitive way. Let's see. So the solution that was, proposed in this project was to, first I can identify where the human's hand is in their a kind of 6 degree of freedom space. So where the person's hand is relative to their body, as well as what the orientation of the hand is. Now the robot and the human both share this, this aspect in common. The robot has an end effector where its like gripper is. And that, that also is like kind of existing in the 6 degree of freedom space, somewhere relative to the robot's body. So the person controls the robot by moving their hand as if it was the robot's end effector. And then a procedure known as inverse kinematics is used to figure out how to move the joints of the robot's arms to be able to actually implement this, getting the robot's end effector to the correct space. So show a video of what this looks like in practice. So you have here on the left, you have a person is just controlling the robot arm by moving this joystick around. The joystick is just, showing how the human's hand is moving through, moving through space. And then that's mapped to how the robot should move its hand to be able to complete the task of, inserting these rods into the holes. And so you can see like the person's arm is very different than the robot arm, which is being used here. But through the inverse kinematics procedure, they're able to figure out, exactly how the robot's joints should be moving to effectively control the robot. So in another project, oftentimes we might want to deploy robots in settings where a human operator can't be directly there observing how the robot's, interacting with its environment. So in this project, they were looking at how to kind of autonomously provide a good camera viewpoint for remote teleoperation of a robot.
I'll show you what this looks like in practice. So on the left-hand side, you see what the operator is seeing. The operator needs to have a camera which is trained on the robot's arm and be able to see like kind of relevant features of the task to know, to know how to control the robot arm effectively. Now, what's happening? The robot that's actually doing the task is in a different room, and there's another robot which is actually providing the viewpoint, and this viewpoint has to be given in a way which is actually effective. You don't just want necessarily a static camera at all times, because that may not control the workspace, may not be able to view the workspace very well. So instead, this other robot arm is kind of autonomously adapting where the camera goes to give the human controller like an informative viewpoint for completing the task. And it's just one more kind of example of this, how can humans better control robots? Here's a video of, this is called bimanual control. So let's see, this will come up in a second, but what's gonna happen here is that we have a person who's gonna be moving their hands to do a task. They're actually just kind of like mimicking how to do the task without actually controlling objects. So you can see this person on the left, they're wearing some special gloves and demonstrating how to accomplish a task. And through the motions that they're making, it's actually controlling this very complex robot, which has arms very different than, the arms of the robot are very different than the person's arms, but just by tracking the hands of the person, we're able to control the end effectors of the robot and get it to do the task. So this is what this looks like, showing how these devices that the person is wearing are actually able to capture the hand poses. And this leads to, being able to figure out how the robot should move its arms to accomplish the task. So, these works are like showing kind of more intuitive ways to control robots by providing naturalistic interfaces for humans. So that's some work which, has been done by professors Yudong-Madison and Mike Gleischer. Another kind of big robotics collaboration, which is happening on campus, this involves professors in other departments outside of computer science, is a very large project with NASA and Boeing, with trying to improve how humans in a manufacturing setting are able to work alongside robots. So just for some context on this project, like at a major airplane manufacturer like Boeing, people are doing very demanding labor. In fact, from talking with one of the students working on this project, they said they went out and they talked with people at Boeing, and they were saying, that oftentimes they have a very high rate of people needing to go through some type of surgery to repair some muscular damage, which occurs due to the physical demands of the work. So the goal would be that if we have robots don't they can lift much heavier objects, and so in principle they should be out on the manufacturing floor trying to take on more of this demanding work instead of having humans do it. But it turns out that in making an airplane, you still need very kind of fine grained control. You need a human's judgment to be able to deal with many situations which come up. So the goal of this project is to improve the work situation for a person by getting more, allowing robots to be more involved and actually letting the human workers and the robots collaborate to perform a task better. So where the human is able to provide more of the kind of subjective guidance for the robot, where it might be hard for a robot to say detect a defect which is happening during manufacturing, but then the robot can do a bit more of the more hard manual labor. All right, and then just as kind of a final example in the the human robot interaction space, this is some work done by Professor Yudong-Madison and a collaborator in, I believe, psychology, on designing social learning companions for children. So the goal in this project was to design a companion, this robot here, which just it can interact with the person through a face. So the robot has a face, so it can kind of convey emotions, as well as having a touch screen interface. So the goal is that this robot can help motivate children to spend more time reading. One thing which kind of comes up in this research is that you envision one possible use, you design this robot and you envision how it will be used in practice. But then once you get to deploying it and like actually sending this robot like out in the wild to be used with actual children, you find that they use it in very different ways than you intend. Like not just like, you know, setting the robot on a table, but maybe like sitting on the floor or just moving the robot all around and like spreading out objects in different ways. So, you know, in this research, they're able to, you know, do a study and, you know, show that like actually deploying a robot was able to like, when children went through their reading activities with some guidance from this robot as well, that they were more motivated to read and they believed that their comprehension improved over time as well. So it's a pretty cool way of like using robots where like maybe there's like you don't have the possibility of like having a teacher always present, but having a robot to be able to kind of help provide encouragement to improve learning outcomes. So the last thing that I want to talk about is my own research, which is more on the side of combining machine learning with robotics. So one of the main goals of my research is to develop autonomous robots that learn to take actions to reach their goals. And so my research focuses on reinforcement learning primarily. And I'm really interested in scaling reinforcement learning to challenging real world tasks. And so one of the robotics projects that I'm starting here is to use robot soccer as a motivating research challenge. Robot soccer is a really interesting task because it happens in the physical world. So it's like a real robotics platform. The task is both collaborative and competitive or adversarial because you have both teammates and opponents. And it's extremely, kind of the reinforcing signal for reinforcement learning is extremely sparse, which makes learning very difficult. So to scale reinforcement learning to interesting problems, you know, like real world robots, I'm particularly interested in improving the data efficiency of reinforcement learning, covering, and so some topics that I've worked on in the past and I'm continuing to work on here are sim to real reinforcement learning, where you train a robot first in a simulated environment and then transfer it onto a physical robot. Better data collection for reinforcement learning, transfer and multitask learning, being able to learn from other agents, and then also safe deployment of reinforcement learning so that when you deploy a reinforcement learning algorithm, you know that it's not going to you know, perform very poorly and maybe, you know, once your robot's taking real world actions, those actions lead to bad effects. So to show I'll conclude with a few videos from my past and some of the ongoing research here. So in previous work that I did, this was actually done during my PhD, we showed how to use a simulator to optimize the walking speed of a robot for playing soccer. So this is the learned walk. We got this robot to walk faster than anyone had been able to manually program it to, you know, walk before by applying reinforcement learning entirely in simulation. As a related work on this, the same direction, we're now trying to scale this paradigm of learning and reinforcement learning to much more complex tasks than just walking straight down a soccer field. So this is some kind of like very recent work that we're doing here, where we're trying to get this robot to like learn how to actually dribble and score goals on a soccer field. So what was really cool here is that all of the learning, this whole behavior that's being shown here is just being generated by a neural network, which was trained with reinforcement learning, whereas traditionally people have approached like developing very similar soccer skills by you know, manual design of finite state machines. So this was all done with reinforcement learning, and we also did it without any reinforcement learning directly on the simulated robot. We actually used like a much simpler simulation that we can run with very little computation overhead. So like one more example of some of the learning robotics research, which is going on here. Another direction is, can we use simulated environments to discover interesting structure, which makes learning much more efficient on a target environment. So in some ongoing work, which is about to be submitted for publication, we're looking at, can we discover what we call latent action spaces for a robot to use? So in this first video, we have this ant-like robot, which is walking, and this robot has 8 different kind of continuous control variables that it has to set at every moment in time to be able to walk forward. And so it has to learn how to kind of synchronize all of these different, learn how to synchronize these 8 different control signals to be able to move forward in a walking motion. But what we're able to do is, in a simulator, we discover that even though it's controlling 8 different, taking kind of 8 different actions at the same time, the structure in how the actions are taken actually allow the robot to be controlled with a much simpler control space. So we use a simulator to discover this, and it makes the reinforcement learning problem much easier because now we're only, in this example, have to learn to take 3 different actions at the same time. And you end up getting like a very similar performing agent in the simulated environment. But then we also find that if you try to transfer your learning to a different target environment where we're training the agent to perform well under a variety of conditions, you end up getting much faster learning. So in this case, this is the agent trying to walk uphill instead of just walking on a planar surface. And it's moves a bit slower, but once we train it with this latent action space, we end up getting a much higher performing control policy. So with that, I'll close. So I know we're trying to have a quick break before the next talk. But if you want to learn more, there's this webpage, robotics.wisc.edu, you can check out. And also want to point you to, we're having a robotics open house from 3 to 5 p.m. And then there's also an HCI open house, which is tomorrow. And so I think some of Bill Gay and Mike's students will be at both the robotics and the HCI. Some of my students will be at the robotics open house if you'd like to talk more with them. So with that, thank you. And I'm happy to take, if you want to like email me questions, happy to, respond to those.
Josiah, you might as well continue if you want, because we're almost at the end of the break time. So
sure, I'll see. I think Yudong, do you want to share your? I think Yudong's here. Do you want to share your screen? Because I'm not sure why I could not project my slides well.
Can you hear me?
Yes.
Yes, let me try to share. I need a different computer. Okay, can you see the slides now?
Yep.
Great.
Okay. All right. I'll get us started then. So, continuing. So as I just said, I'm Josiah Hanna, and this is Yudong Chen. So we're representing the machine learning group here at UW-Madison. All right. Next slide, please. So yeah, first of all, welcome virtually. So these are some, some photos our colleague Sharon Lee took, showing what Madison looks like since you can't actually be here in person. So this is the summer and the fall. You can see it's a very beautiful, very beautiful city. Next slide, please. Okay, so artificial intelligence at UW-Madison spans a number of different research areas. So you just heard from me talk about robotics. And so most of what we're going to focus on today is machine learning. But then there's also a computer vision talk, which Yong will be presenting at 11:45. And then we also, there's biomedical informatics as another area under artificial intelligence. So here is, some of the faculty working on, areas related to AI and machine learning at UW-Madison. So this is not just computer science. It's, but I think, a lot of the top row is the computer scientist. But then also we have colleagues in ECE, mathematics, industrial systems, and, other statistics, and, many other departments. So within the, all of the artificial intelligence, you can learn more about the machine learning research happening at UW-Madison by going to this page, machinelearning.wisc.edu. So the machine learning group, again, it brings together people, research and the courses that are both focused on like theory and like foundations of machine learning, as well as people that are using applications of machine learning within their research. Maybe they focus on like, an activity like marketing or healthcare, but they're really trying to see how machine learning can be used within those disciplines. One kind of main, if you're interested in these topics like related to machine learning, I'd highly recommend you to attend the weekly seminar SILO that we have. SILO stands for Systems, Information, Learning, Optimization. And if you're interested in kind of seeing a more in-depth research talk from like a number of our faculty, oftentimes faculty at UW-Madison present at this seminar as a way to kind of keep their colleagues informed about what their research activities are. But then also there's sometimes, external speakers doing like really cutting edge work in these machine learning related topics. Okay, so these within computer sciences, these are kind of the main faculty doing, machine learning research. So there's Yudong, who you'll hear about his work. There's also, our colleagues who are doing optimization, Ilias and Jelena and Steve. And then there's myself, there's Professor Sharon Lee, Fred Sala, Yong Jae, who will be presenting computer vision, and then Ying Yu and Jerry. So I guess with that, I'm going to hand over to Yudong, who's going to go in more in depth into like what all the different faculty members work on.
All right, thanks, Josiah. Let me just give me one second. All right, can you still hear me? Okay, great. So I'm going to give a very brief overview of the research done by the faculty members in the machine learning group. I think you already heard from Josiah on his work in the intersection of robotics and machine learning, so I'll just skip this. And then I'm going to present the research of several other faculty members roughly in the order of when they joined the department. So Professor Jerry Ju works on several foundational areas of machine learning, and he actually won some major rewards in machine learning, including the ICML Classic Paper Award. And one of the main themes of Jerry's recent research is in machine teaching, which you can think of as the inverse or dual problem to machine learning. So machine teaching concerns the following question. So suppose you have a teacher who knows what the goal of the learning is. You know what the target model you want to learn. And the question is, how do you design what data you can give to the algorithm so that the algorithm can learn this target model in a quick and efficient way? And in many settings, the optimal design of the data is not ID data. You want to design the data in a correlated and smart way. And this machine teaching techniques obviously has many applications in education, in psychology, and also in computer vision. And another area that Jerry is interested in recently is the so-called adversarial machine learning. So in this adversarial setting, you have an adversary who can manipulate the data, for example, or manipulate the machine learning system in some other ways. And the goal of the adversary is to try to force the machine learning algorithm to make mistakes. He's trying to mess up with the learning process. So Jerry is interested in understanding when this is possible, why this kind of adversarial attack happens, and how you can be robust against this kind of adversarial attack. So his research covers both attacks that are on text time, attacks on the text data, attacks on the training data, and other subtle forms of adversarial attack. And obviously, since machine learning is used in very critical applications now, like driving a car, having this kind of robustness is extremely important. And next, I want to introduce Professor Ying-Yu Liang, who is interested in many foundational theoretical questions of machine learning. So one of his recent focus is in the understanding deep neural networks. So we all know that neural networks has made some impressive empirical success in several areas of machine learning, including vision and reinforcement learning and natural language processing. But why deep learning works remain a mystery to a large extent. We all know that training a deep neural network involves solving a highly non-convex, highly nonlinear problem. And sometimes you can even train a huge neural network model with more parameters than the number of data points you have in the data set. Conventional wisdom will tell you that this won't work, you will overfit, it will take a long time to train. But in practice, it seems like very simple algorithms like stochastic gradient descent works well. So Ying-Yu is trying to understand why this is the case and why neural network is successful despite of this highly non-linear and non-convex nature of the model. And in a different line of work, Professor Ying-Yu Liang is also interested in robust machine learning. So here, Ying-Yu wants to design algorithms that will work even when the test data is different from the training data. And on this slide, you can see this example where an attacker is able to change some important features in your images. So using a naive standard algorithm will have a very different output if your image has been attacked this way. But Professor Liang is able to design more robust algorithms that still give the correct desired output, even when you have an attacker that modify your image and change the features in a very subtle way. Professor Sharon Li is our expert in deep learning. So Sharon is broadly interested in many problems of using deep, large-scale neural networks, and particularly in this so-called open world learning paradigm. So what is open world learning? So suppose you are trying to use a machine learning model like a deep neural network to in a self-driving car. And when you train a self-driving car, perhaps you mainly train your car in a city. So your training data has many urban driving scenes, driving on the city road networks. But now suppose you sell your car and your customer take the car to a road trip and drive on a rocky mountain road. So in this case, your test data is very, very different from the training data. Since you have human in your self-driving car, you want your algorithm to be robust against this kind of distribution shift in the test data. So Sharon is interested in achieving this even when using complicated deep neural network models. And in particular, Sharon is interested in detecting when the test data is different from the training data. Sharon is interested in quantifying how different they are, and he's interested in developing algorithms that are robust to this kind of difference. And her algorithm has many interesting applications in several critical areas like healthcare, computer vision, and self-driving cars. And Professor Fred Seller also works on several foundational areas of machine learning. And one of the questions that he would like to answer is to understand the limits of machine learning, what machine learning can do, what machine learning algorithm cannot do, and hopefully by understanding the limit, we can also extend the limit, extend the scope of what machine learning algorithm can do. For example, one major bottleneck in many machine learning paradigm is how to get label data. If you want to train an image classifier, you need data sets that consist of many images with labels that tells you is this a dog image or is this a cat image. And obtaining label image like this involve human. You need a human to do this, to label the image. And this is a very time-consuming and costly processes. So Fred is interested in breaking this bottleneck using the paradigm of so-called weakly supervised machine learning. So you want to combine data set that has these labels and data set that doesn't have labels. It's much easier to obtain unlabeled data sets. And Fred developed various approaches to train a machine model when combining label and unlabeled data. And another question that Fred is interested in is to understand the role of geometry in machine learning. So many of the machine learning algorithms, standard machine learning algorithms, relies on the Euclidean geometry, the geometry that you're familiar with. But Fred showed that for some more complicated problems, non-Euclidean geometry actually is more suitable and enables us to develop more efficient algorithms that can learn more complicated structures. And finally, to myself, so my research area lies in the intersection of optimization and machine learning, and also a bit of statistics. So one half of my research involved using optimization to learn a good model. And we all know that, and as I mentioned several times, modern machine learning often involve hard non-convex optimization problems like training neural networks. But people are still solving this kind of hard problem on an everyday basis, and sometimes it works really well. So I would like to understand why you can solve these problems despite these problems are hard, provably hard in the worst case. So some of my research shows that even though the problems are hard, apparently you will be able to approximate them by easier problems. You may be able to approximate non-convex problems by convex ones. Some of the problems are hard on the surface, but they may have hidden structures that enable you to find a good solution, even though a naive algorithm only finds you a local minimum, a suboptimal solution. And some of my research also shows you that even though the models is very complicated, the optimization problem is non-convex. Some simple algorithms like gradient descent or greedy algorithms or EM works well, both in theory and in practice. And the other line of my research concerns the dual problem of using machine learning for optimization, for making optimal decision making. So in this line of work, I'm interested in reinforcement learning, particularly the theoretical foundation, the theoretical side of machine learning. I'm interested in understanding questions of what is the sample complexity for reinforcement learning, how many data points you need in order to learn a near optimal policy. What is the power and limitation of using function approximation architecture in reinforcement learning? What is the role of nonlinear model in reinforcement learning? And how to use reinforcement learning to solve hard sequential decision-making problems. So for me, I'm particularly interested in applications in network scheduling and resource allocation. and other operation research type problems. All right, so these are the faculty members in computer science in the machine learning group, but we also have very close collaboration with other faculty members in other departments, including the electrical computer engineering, biostatistics, mathematics, and the Department of Statistics. So I'll just briefly mention a few of our colleagues in the other departments. So Dimitri, who is my colleagues from ECE and my friends from grad school, has done a lot of interesting work in distributed learning, how to train large-scale machine learning algorithm in a distributed way. And his more recent research also includes robust learning and adversarial learning. And Professor Rob Lowak, who is our distinguished colleague also in ECE, is an expert in active learning as well as many other research areas. He has done so much work in so many different areas that I simply don't have time to list here. And we also have many other collaborators who works on biomedical applications of machine learning, including our friends from the bioinformatics departments who works on biological networks, gene regulation, using combinatorial optimization to understand DNA sequencing, and using NLP to predict disease risks. So many interesting applications in biomathematics. That's my presentation. I hope you continue enjoying this virtual visit and do meet with our faculty in our one-on-one meeting. Thanks.
Thank you, Yudong. And the next presentation will be up as soon as they're ready. Young-Jae Lee.
Yes, I am ready. Let me try to share my screen. And I actually have a video, so I'm going to share my sound. Okay. Let's get started here. All right, so first of all, congratulations everyone on being admitted to our computer science program. I hope that you've been enjoying all the meetings and presentations so far. So I'm Young-Jae Lee. I'm an associate professor in the computer science department. I work on mainly computer vision. And what I'm gonna do is start by trying to entertain you with a 1-minute video. Okay, so this is a video presentation of a recent work a couple years ago that we did in my lab. All right, so let's start with this. So there is gonna be sound. Okay, so if you come to our university, you can not only do cool research, but learn to make cool videos like this, okay? So all right, so For those of you who aren't familiar with computer vision research, let me just start by giving you sort of a quick overview. So there are many different problems in computer vision that we work on here. I'm just listing a few, like image classification, semantic segmentation, object detection, human pose recognition, trying to understand 3D information from 2D images, and also doing like 3D object detection. And there are many different applications. For some examples are self-driving, vision systems in automated retail stores, digital painting for graphics applications, medical imaging for medicine and health, face filters and augmentation, and agricultural applications. And our field is highly interdisciplinary, so we use tools and collaborate with researchers across a number of different areas, including, of course, computer science, statistics, optimization, electrical engineering, physics, and hardware devices. And at UW-Madison, we have 4 faculty who work in computer vision. So they're Mohit Gupta, Vikta Singh, Jin-Yi, myself, and we will also have Professor Pedro Regado, who will be joining the EC department in fall 2022. And we have currently 20+ students working in computer vision. So we have a pretty large group here, and we have also regular meetings and collaborations across the different faculty groups. And so I'm going to start by introducing a few of the research projects that we do in my lab, and I also talk about the projects that are done in the other labs. So again, I'm Young-Jae Lee. I'm an associate professor in the computer science department. My main research areas are in computer vision and deep learning. And my high-level research goal is to try to create systems that can learn to understand visual data with minimal human supervision. So over the years, I've worked on a number of different problems within computer vision, including image and video recognition, image generation, privacy preserving recognition, object detection, segmentation, trying to understand video data captured from wearable camera, and also other interdisciplinary applications with collaborations with both graphics researchers as well as veterinary science researchers. And we regularly publish in the main computer vision and machine learning venues. And some examples of some ongoing projects include generative modeling for image and video generation, self-supervised learning, semi-supervised learning, video understanding, point cloud understanding. So this is trying to understand data captured from depth sensing cameras or LiDARs, object detection and segmentation, multimodal learning, domain generalization, and many others. And next, I will introduce Professor Mohit Gupta's research. So Professor Mohit Gupta is a computer vision faculty who works in computational imaging, designing novel cameras and vision algorithms for applications in robotics, interfaces, and scientific imaging. And this is Mohit. And one ongoing project in his lab is on developing computer vision and machine learning techniques for this emerging and exciting kind of camera called single photon cameras. So these are cameras that are extremely sensitive down to individual photons. And for the first time, they can enable vision systems to perform well in extreme conditions such as extreme dark. And these are now starting to become mainstream. For example, the latest Apple iPhone has single photon sensors for 3D imaging. And this work has resulted in several publications and patents, as well as industry collaborations. And one of the lab's broader goals is to develop computer vision systems that can work reliably in challenging real-world conditions, such as outdoors in dark and strong sunlight, bad weather, underground, so that computer vision systems can be deployed in the real world for practical impact in applications such as self-driving cars, augmented reality, and many different aspects of robotics and automation. So next is Professor Yin Li. So he is a professor in the biostatistics and medical informatics department with an affiliate faculty position in computer science. His main research areas are in computer vision, wearable computing, biomedical data analytics. And his main research theme is to understand human activities and their health implications by analyzing videos and wearable sensor data. And a few of the recent ongoing projects include a number of different topics in video analysis, such as using or developing new deep learning techniques for first-person action recognition, for surgical video understanding, for creating systems that can learn from both visual data as well as text data. And also a few threads on wearable visual sensing, where he has collaborations with researchers at Cornell and Purdue on wearable hand tracking, adaptive video analytic systems. And if you're interested, you can check out more of his projects on the website that I've linked below. And then finally, we have Professor Vikas Singh. So he is also a professor in the BMI department with an affiliate position in computer science. And his research areas are in computer vision, machine learning, statistical image analysis for imaging and data analysis problems in biomedical sciences. And some recent ongoing projects include how to create machine learning models that are more fair and can also learn from data sets spanning a number of different modalities, including, for example, visual data, text data. He also has projects on diffusion and differential equations, how to make machine learning models more efficient, including the more recent transformer architectures, trying to have better uncertainty and calibration estimations for the ML models, and also research on non-decomposable losses in computer vision and in medical imaging. So a couple of examples include, for example, for fairness, if you're trying to create, let's say, an algorithm that can, given an image, say whether the activity is of, let's say, cooking, you would like the model to focus more on the relevant objects like food or pans and pots and so on, rather than whether there's a particular gender person in that image, right? So this is a particular example of what we mean by trying to create more fair machine learning models. In terms of harmonizing scientific data sets, his group has ongoing work on trying to learn from both visual data as well as text data on trying to create these systems that can help us to diagnose, for example, aging, Alzheimer's disease. And this is a project that is in collaboration with a number of different institutions. So that is all I have for today. So again, congratulations on being admitted to our department and university. We really hope that you will join us. And if you have any questions, feel free to email me offline. You can Google me and you'll be able to find my website. All right, thank you.
Thank you. Thank you, Young Jae. Yeah, I want to learn to make videos from you. So next up for the rest of the faculty talk section will be Yea-Seul Kim. So Yea-Seul, take it away.
All right, I'm gonna share my screen. Can you see my screen? Probably there's like a not contents on it.
Yeah, we're seeing the motion W.
Okay, yeah. Great. Okay, so my name is Yea-Seul Kim. So I'm gonna today introduce our group. Probably its official name is graphics, but our group does a little more than graphics. So we try to characterize ourselves as a visual computing group. So I'm going to speaking for today about my work, but also Iftikio and Professor Mike Lesher as well. So here I want to introduce a little bit. So by nature, I think you'll get the sense of like how interdisciplinary of work of ours, but things that are not in our group, we're interested in graphics and visualization. Visualization here is like charts and graphs, like kind of abstract data representations and so on, and simulation and animations. But beyond that, there are some other works that kind of overlap with the other group as well. Yong just presented here, but computer visions and robotics and multimedia, VR, AR, and even HCI, our work is kind of overlap with those groups. By the way, I'm going to introduce, I'm a part of like HCI group as well, so I'm going to present about that group after this talk. So 3 of us are in this group. So me, myself, and Iftikio, and Mike, and there are many other researchers in this campus actually doing similar work, for example, in mechanical engineering, psychology, and design studies, and so on. So we physically located as a faculty, I think, on 6th floor. You haven't been here, so it's hard to like picture how many floors in this building even. I think we have 8th floor, if I understand correctly. I'm a kind of new faculty. I hired during the pandemic. So it's a reason that I actually went to my office. But anyway, we're all in 6th floor. And then there's a 2 visual computing lab and robotics lab in the 1st floor. So this is kind of snapshot of a visual computing lab. And this is like robotics lab. Actually, there's a robots, some facility and some displays and camera, those fancy things located in the 1st floor. So I'm going to introduce the Professor Iftikio Sifaki's work. This statement is very succinct, succinctly summarize what he's doing. So his work is about modeling how systems in our physical world look and function, explore laws and algorithms that govern their behavior, and finding opportunities to make things faster and more scalable by cube math and modern parallel computers. So I'm going to unpack what this means by providing a few example project. So this one is, he has been working on the computer-based simulation of digital human body. So one second, let me just reorganize stuff. So yeah, he has been worked on this simulation of digital model of human body with a particular focus on digital actors that move under the action of biological muscles and how such motors are controlled to achieve certain high-level tasks. Another project, he called it this as like a visual effect applications. So he has worked on a number of techniques that have been used in animated feature films, including simulation of fleshy characters or where the skin shapes are generated kind of automatically via simulations and modeling of hair dynamics and so on. So in a partnership with clinicians, he has created some interactive virtual training platform for plastic surgery, so which allows surgeons in training to review and rehearse the procedure in a very non-invasive setup. Both for the visual effect application as well as this virtual surgery examples, geometric process such as cutting or slicing or like breaking object is essential and crucial, right? So he has worked on this geometric algorithm to facilitate this whole process. In the recent year, he has worked on some scalable simulation for topological optimization tasks. So in this discipline, the concepts from numerical optimizations are used to generate some structures and mechanisms that exhibit some desirable mechanical properties, such as a breach with optimal strength and minimal material used, and so on. So finally, he has been very active in this area of facial animations using computers and has worked at UW and in industry with groups that are active in the acquisitions and reanimation of digital human faces, often with the objective of automatic creations of digital actors, either from biomechanical principles or using machine learning algorithm from large volumes of performance capture data. All right, so I'm going to introduce about Mike Fleischer, our next professor. His work can be characterized as three different areas. So first, human graphics interactions. So basically concerning, can we create the tool so that the people can easily author the pictures or data or animations. The next domain will be human data interactions, which is like mostly visualizations with visual analytics tools and interactive learning and so on, concerning how human perceive the data, how human perceive the visualization, and how can we investigate the interactions between two parties. Lastly, he's done some work in human robot interaction. Of course, it involves lots of robots. All right, so the first part of it here, like human graphics interactions, he's interested in how we can make tools that make it easier for people to create artistic things like animations and video and so on. So imagine you're not an expert in creating those animations, but this tool allows users to manipulate minimally, like we're using a lot of GUI and very user-friendly interface to author a high-quality animations. And authoring tools that automatically transform the video to make them easier to watch, such as implementing some features like automatic panning and zooming and so on. So next kind of pillar of his research is about human data interactions, about visualizations. What he does is those three different area of research effort. The first, we can say visualization research, which is understanding how people perceive the data and visualization so that we can kind of understand the process of it, how we can understand what is the designing principles, how should we design effective visualizations and so on. Those are kind of covered by this visualization research. Another aspect to it is visualization practice, meaning that the visualization inherently concern about the underlying data, right? So there's millions of data out there. Sorry, my cats are crying, so I'm distracted. So the visualization practice concerns about how can we visualize data that suits for a specific domain, let's say. So for example, think about security log, the millions of lines and millions of data there. How can we build a tool so that security researchers can kind of parse their data better, like get insights into it? So we often work with the domain experts, like domain scientists, who has all this data, and then this practice concerning like building tool to help them to understand their own domain specific data. The last one is about visualization education. So as we're living in a data-driven society, right? So the visualization is everywhere. We have like data everywhere, but it only makes sense to visualize. You can only make sense of the raw data by visualizing it. So I mean, if it's a simple data, a few lines of whatever, then you can just eyeball it. But beyond a certain threshold, like we always have to visualize to understand. So, but then there's certain way that actually make things easier for lay individual to actually create the data. So visualization education is one of the pillars that visualization researchers actually working on. So I am doing a lot of visualization work as well. Professor Mike Fleischer also doing a lot of visualization work. I want to introduce briefly about what is visualization research is about. It can be many things, and of course, any field has a different taste of research, different aspects, or different even the subdomain within a domain. So here's like 4 different examples. Actually, I have a few more next slide, but here's a few examples of different type of visualization research. So first one is about perceptual studies. So I brought one very seminal example. So you see this with the pie chart and bar chart here. So this was very, I think it's date back to like 30 years ago or something. It's a very kind of initial work in this visual perception work where a group of researchers try to understand which types of chart is actually better for certain tasks. So they recruit a group of people and then ask them to complete this task, which is following. So first you have to identify the biggest portion of each chart, which is apparently D, right? D part is the largest and then the longest. And then you have to make a guess or estimate what is the ratio between the largest portion and the A, right? And the ratio between A and D and B and D and C and D and E and D. And of course, the same things on this bar chart as well. So what is the ratio between A and D, B and D, C and D, and D and E, and so on. And apparently after you can actually calculate the accuracy because there is a ground truth in front of you, it turns out that a lot of estimations are way more accurate when it's done using bar charts. I'm not sure you've heard of like pie chart is bad, pie chart, you don't use pie chart, blah, blah, blah. Those arguments are kind of around this community, but there is actually scientific evidence that why bar chart is better at decoding the value compared to the pie chart. So those are, you can easily imagine this types of approach can be expanded with other chart type, right? Other charts or different contexts where, oh, you want to know what is the perceptual difference between two graphical objects. You recruit people and ask them to do certain things and then prove that certain representation is better supporting the task or not. Another domain will be kind of technique design where more and more data becomes available. There's like a very unique consideration for each data, right? So for example, some data are hierarchical, some data has like a node to it. So visualization researchers often come up with a new technique that kind of support those data types and so on. So these are the different, I'll say, domain of data that visualization researchers particularly care about. So as you can imagine, this literature and text, imagine it's not a number anymore. So it's a bar chart and the pie chart, it all encodes kind of numerical value. But when it comes to text or document, you probably need to implement a different strategy. So a group of researchers also work on how can we visualize this text effectively by considering different modeling approach and so on. And also recently those many of the big neural model produced a very high dimensional vectors for this word embedding and so on. So there's a very active area. How can we visualize those models? How can we reduct the dimensions so that we can present all in a 3D or 2D plane and so on? Those are the kind of active area as well. And obviously the genetics, it has own constraint in their data. It's by nature, it's very sequential. And then the task that domain scientists wants to carry will be very different from others. So you can imagine a tool that actually very supportive on those specific part of data and the task and so on. All right, so this is one of the Mike's work that he's done, some of the building tools or system over the year that help people work with the data in a different context. For example, this Snowcat project is about control automated ML models, and some various other projects that kind of gets at how can we support the developers who train the model or wants to use that model, use the complicated model, so to support those tasks using some visual analytic tools. So this is one of examples of Snowcat. It's a snapshot of the Snowcat. And also he's very interested in robotics as well. So some of his work is at the intersection of visualizations and robotics. And he explores how to help people understand what robots can do and work with how to simulate models in VR to understand what it'll be like to work with them. All right, so, and they work with, he actually worked with a real robot. I think this is coffee robots, probably he's drinking something coffee that's made by robots. And the major thrust in his work is to build a system that allow people to operate robots by real-time control. So a key approach is mimicry. So where the model mimic what the operator does. So imagine this is a doctor, this is the surgery robot. Then the doctor can kind of prescribe by doing it, and then the robot kind of mimic what doctor would do so that they can kind of take the good thing about both worlds, where doctor has expertise and robot has very sophisticated manipulations of the object. So he's very interested in the problem of how to provide awareness to the user, how robot works. So basically this user is kind of manipulating this manipulation robots here, but this camera robot is kind of follow the movement so that user can actually see what's happening using the robot's view. All right, so he's been exploring some haptic feedback as well. Also, his group worked on some methods that allow people to demonstrate what robot can do and what robot not to do. So by kind of showing the task that they can do and tasks they cannot do. So these are the things of his work, and I'm going to briefly introduce about my work. I'm mostly interested in how to make data more accessible to people with varying ability. For example, some might have some disability, such as like visual impairment. Some might have no statistical literacy or statistical background. Those are the kind of my aim at like supporting all these lay individuals, possibly with some disability, to understand the data and the visualization better. So some of my work concern about incorporating some of the user's belief, because a lot of times you already have some prior knowledge or prior beliefs that kind of govern what you're seeing it. So I've been working on kind of modeling where can we incorporate people's prior belief into the interpretation process so that we kind of understand what they will end up believing after reading visualizations. And recent work mostly fall into this category, accessible visualization, how to present the data to those who cannot see. So my first project about this region was about how to formulate alternative text for visualizations. So probably some of you are familiar with those blind individuals use screen reader to parse all the information online. So if there's no alternative text, then they wouldn't even know this is actually a visualizations or charts or anything. So our group kind of investigate what are they want to know when it comes to visualization. How should we formulate it? How should we formulate alternative text so that they can understand the visual better? Now we're working on kind of automatic pipeline that like kind of know what's in there and detect it automatically, and then formulate the automatic alternative text for them. So another project, so actually kind of over time, but I'll just keep going because next session is also about my work and so on. So this one is about tables. So tabular representation is really common in online, probably like kind of very popular, followed by like bar charts. It has a lot of visual metaphor that help sighted people to read these things. So for example, here's like a merged data, right? Merged cell. We immediately know that, oh, each cell has all the same information. And then there's empty cell, we immediately know that it's a missing value. And there's like a entire merged row. We kind of perceive this as a separator. Oh, that there's like two different tables. But if you're if a user is using screen readers, it becomes so complicated to construct this mental model because screen readers are pretty linear. And then once you get in the cells, nothing gets said. Then like this people get so confused what's going on here. So we do a lot of interview and then kind of human-computer interaction methodology called like kind of formative semi-structured interview to identify what is the inaccessible components in this table reading. So we identify those and then we create some Chrome extension to automatically detect those and then transform that into accessible one and then inject back to their browser so that when they encounter any table online, all the things will be pretty accessible to them and then it's easy to read and so on. So those are the kind of system building work that I'm doing to support this populations. Yeah, so these are the class that we're offering and you can find this in Explore in this email as well. All right, so I'm going to move on to this human-computer interaction. So this my work is kind of intersecting between like human-computer interaction and visualization. So I want to introduce briefly about what HCI is. So basically, there's three components involved. And this is kind of simplified view, of course, but there is a task. You want to achieve a task. For example, you want to book a hotel. Whatever you want to do something, let's say, and then previously, if there's no computer, then like you have to call them, you have to like drive by. But now we have a computer here. That computer can give you some tools or system to complete that task, right? And doing so, human and computer kind of interact with each other. Those are all the things that we're concerned about. For example, you're blind individual, you want to cook, let's say, then your task will be cooking. And the computer can be kind of VR devices where it's kind of supporting those activities. You can think of anything, any interfaces, any system work. Those are the kind of, you can kind of characterize those work with these three components and three entities and think about how this HCI is very concerning about how should we design this interaction so that the human can complete their task accurately and effectively. So many people says a little differently. As you can see, the HCI, some says like HCI is the intersection of engineering, computer science, design, and psychology. Some says like computer science, human factor engineering, cognitive. Maybe what that means is that you can find this diagram, like millions of diagrams out there, meaning that it's very interdisciplinary. So I think the fact that there's so many diagrams already kind of indicates how interdisciplinary they are, but still like we leverage a lot of computer science knowledge, but also like human knowledge as well. Like how should we understand human? How can we prompt the human so that they kind of know what they want? How can they express their needs and preference to the computer? And so how can computer should interact with the human? All this knowledge comes from very different background. So I'll say it's very interdisciplinary field. And beyond, actually, we have 3 of us in this group, but beyond us in this campus, there's just so many people are actually doing this HCI plus design research. So if you're interested in, you can look it up. But today I'm going to focus on these three of us' work. So Bilge, sorry, there's a waiting room. I'll just meet them. All right, so I'm going to talk about 3 of us' work very briefly. Since let me go next page. So Yuhong Zhao, the professor Yuhong Zhao, mainly doing a lot of accessibility work using AR and VR, but she's also interested in mobile interactions as well. I'm going to share you a couple of demo video from her work. So this is a design and build intelligent interactive system to enhance human ability. So imagine you're blind, low vision individual. So and then you're at the grocery store. You have to think about what you want, but you have to like locate those things. So in this case, you want to locate some snacks, I guess, certain snacks. Let me just play this video. All right, so it's basically the user indicates what they want, and this VR application search it and locate it, and then give a cue so that the user can actually find it more easily. So this is one example of accessibility work to support the low vision individual who can find the object, everyday object easily. Another project is about indicating the stairs. So if you're a low vision individual, it's really hard to like sometimes it's constrained to step up or down using stairs. So this VR application is actually highlighting the edge so that people can use, or people can confidently staring up and down and so on. So let me just play the video quickly. Yeah, as you can see, so as the user goes up, it kind of dynamically changed the queue as well. But they in their paper, there's various different design applications or design alternatives that user can actually choose from. So these are another accessibility work that she's doing with the VR applications. Another one is address the accessibility of emerging technologies. I'm going to explain a few things here. So this is a project where she's kind of combining her knowledge on accessibility, but also kind of low vision, understanding of this population of low vision. So she suggested all sort of different features. How can we enhance the experience for low vision individuals within just normal, many different VR application contexts? So for example, you can just implement this magnification lens, but also edge enhancement. Since they're low vision, they can't detect the edge well. And there's many different features that you can utilize with the different VR applications. So these are the kind of quick video of how that get implemented in a different scenario. This is just a typical VR application that, and using identified technique by her to enhance the experience of people. All right, so next, let's move on to Professor Bilge Mutlu's work. He's mainly interested in human robotics interaction. So I'm not sure you've heard of his work in the robotics session, but I'm going to explain briefly about his work. So he works on designing some educational robot, actually, to study the long-term interaction with robotics technology. So this is a learning companion model, a robot that his team has built and helped children how to read. So this is another project that's collaboration between him and Professor Aus from our PL group, where they build design and programming tool that use software verification and programming synthesis methods to make robot programming more easier. So if you're novice on programming language, especially for robot, but this kind of like a human friendly interface will get you to the point where you can kind of design the robots actions and different designs and so on easily. So another project he involves is a collaboration with the Faculty of Psychology. They explore ways of making agent emotionally more sophisticated by designing some algorithm and interface that are inspired by some psychological theories of emotion. So the last project that I'm going to introduce today is a collaboration between Professor Yu Hong and Bill Gay. So they started a new project using AR-based interface for controlling and interacting with robots. So you see an early prototype here from his group to program and control a collaborative robot to perform complicated manipulated tasks by using some AR technology. All right, so lastly, again, my work. So I brought some HCI-ish work for this talk because I have a lot of like visualization intensive work, but this is more like HCI's work, but still like you will notice a lot of things are about data. How can I communicate the data with lay people? How can I build a tool to support those data comprehension and so on? I want to introduce a few tools today where I built about this measurement. So sometimes you read an online article and there's a very complicated measurements are presented. So sometimes like it says like, oh, the forest fire burns like 1,300 acres yesterday, but then what is 1,300 acres? It's really hard to contextualize those kind of unfamiliar measurements. So this tool is basically kind of converted that unfamiliar measurements with the familiar measurements so that you can be more contextualized with the context of article, as well as kind of this number becomes more relatable. And I have another project where try to convert the kind of complicated statistical concept with the kind of familiar analogy. I'm going to briefly explain about that as well. Let me just play a demo of this tool where you enter your locations, or this tool can detect your IP address to get your location. And while you're reading this online article, you click something like 4,700 acre and some types of like spatial objects, such as like different cities and so on. Then this tool can automatically generate some of the personalized map here, where you can kind of make sense of, oh, the different cities in India that is very far from each other. It can be contextualized based on my location, where I am in Seattle, and then this is a distance between me and the University of Oregon. So this is the one tool that actually you can use it. It's in the Chrome extension that automatically parse the news articles from the HTML and then detect any spatial measurements and spatial object, and then sort of generate the personalized analogy for you to relate with that numbers and spatial objects. So next one is about, so this is effect size. I'm going to be brief. It can be a little daunting. So there's, I guess, a concept called effect size. Probably you're very familiar with the concept of statistical significance. So a lot of research shows that statistical significance between like two groups, but that's not enough. What is the effect size? For example, the green tea lower your cholesterol. And then probably it's very statistically significant, but how effective? How much they can lower the cholesterol? Is it just 0.001 or like 3 milligrams? How much? That's actually effect size, which is more important than whether it was statistically significant or not. So to practically significant, this effect size should be higher, but often it's really hard to digest the concept of it. And sometimes it represented as like, oh, the effect size was small. But what does that mean by small? Effect size was like coherence D 0.4. It's hard to contextualize those numbers. So in this project, I try to convert that with the familiar analogy to you. So for example, it's very small effect size can be contextualized or like converted to the probability of a randomly selected 16-year-old woman in America is taller than a randomly selected 15-year-old girl. So for example, like it'll be very small differences, right? You can imagine how the difference between those two groups when they randomly get selected. So this was kind of a follow-up with the previous project where like try to contextualize the unfamiliar measurements and complicated statistics better with the personalized analogy. I'm also interested in some models prediction, how to make this models prediction more digestible for lay people. For example, this Zillow has like some estimates on a house price, but probably it's a models prediction, therefore there's uncertainty around that. But we don't often communicate because it's complicated. And of course, some visualization kind of communicate those uncertainty as well, but people don't know how to interpret. So here, like many AI infused applications that we're using these days are entailing all this notion of uncertainty, but they try to make it binary. Is it like yes or no? But apparently there's uncertainty, there's a confidence going on. So I'm working on how to communicate those types of models, uncertainty, models prediction, using some human computer interaction methods or other strategies that I've been using in my work. All right, so this is all I have, and congrats on your offers again. And if you have any questions or other inquiry, just let me know. You can find me in the UW-CS faculty. I have my emails there and so on, so please feel free to reach out to me if you have any questions.
Thank you, Professor Kim. That was very informative. Lots to talk about for you. Thanks.
Thank you.
So that was the final talk of the day, faculty talk. And for all of you that joined us this morning, I want to thank you for coming and remind you about my session tonight at 6:30, which is on the schedule, where you can get any questions you might have answered. And also want to thank our academic program manager, Cindy Fendrick, for ably hosting this faculty talks this morning. So everybody have a good day. I hope you enjoy the open houses and the events tomorrow and hope to see you tonight.